Hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. Today I actually decided, because this has come up many times, that I think today we're going to do a Handmade chat, not a Handmade Hero, because I would like to really clarify this, and it's the sort of thing that comes up really frequently, and I guess, you know, if I had done a complete introduction to C series ever, which I've never really done, which, you know, someday would probably be nice, we would have covered all this sort of stuff. But since Handmade Hero is really only about how to do game programming, and it kind of assumes that you already know how to do non-game programming of some kind, there's a lot of kind of gaps in the understanding potentially about what's going on in terms of how C is doing things, how the CPU is doing things, and so on. And we dive into it at appropriate times on Handmade Hero, but we sort of leave it, as just understood a lot of the times if I'm not specifically addressing it. And so what I want to do is just maybe take some time to kind of go over some things in a little more detail today. I do apologize for people who already know these, but I feel like once in a while it's good to kind of just do a chat where we kind of address some things in detail that people who aren't familiar with sort of lower level programming have a hard time wrapping their head around, and we may have said them on Handmade Hero, but we don't necessarily dedicate a whole lot of time into looking into them other than just stating what's going on and, you know, moving on. So this was motivated by yesterday. I'm going to go ahead and bring up this email here. I asked one of the people on the chat who had been asking some questions on the chat to write in and sort of more completely describe sort of the problems of understanding they were having with a particular thing they had been asking about on the chat. And I was like, just send me a thing and we'll kind of go over it. Because I get this specifically asked about this particular thing actually often. This is not in any way the only time I've been asked about this. And I think that for whatever reason, it's a uniquely confusing aspect of perhaps C, C++, or actually also just perhaps low-level programming in general. And so I just kind of want to go over it here. So I'm going to go ahead and read this. It's not very long. And then I'm going to sort of break it apart and start talking about how these things work and try to really like cement how this stuff happens, so that when these questions are asked in the future, we have an episode to point to where like, here is an episode that explains completely from start to finish everything you need to know about this. So the email goes, hello Casey, I'm Naker314 from your stream, and I believe they are on the stream today as well. Who asked a question about type deafing of functions. I'm trying to follow along with your file IO code. First established in episode 15, then completed in 24 and 25. Not 100% sure, but your file IO code definitely changes from the 15th episode. You use the following lines of your platform layer, and it has what we are all sort of familiar with now as the way that I typically do function pointers if they're going to be defined in multiple places, which is I make a pound define for the function signature, then I make a type def using that pound define. Again, I'm going to go over these in a little more detail later, but that's not the real meat of the question. I think this creates a type called debug platform read entire file that returns a debug read file result and takes a thread context pointer and a char pointer, and that is a correct thing to think. This will allow us to declare a function of this signature as a type and thus a function pointer. In another place in the Winter3 layer, you define a function that matches the signature of the type def that will actually load a file in Windows as, and here it is. I believe the macro changes just to read and then puts that there, and he is again correct writing in. This means you can declare the following: debug platform read entire file star a equals debug platform read entire file. I inserted the star there because it seems it can only be used when we have a pointer, correct? I tried to make it not a pointer in a test program, and a function can't be initialized. The left-hand side of the declaration is what you're declaring in the game memory struct, and assigning it to the same function in the Win32 layer when you initialize the game memory struct and assign members. Forgive me if the terminology is wrong. I'm not from the CS world. As of writing this, I'm getting the vibe that there is no way for a CPP file to communicate with another CPP file without the use of function pointers. I think that's what a callback is. I have to think about this more before I say anything further. I also have some header file problems too, where one is referenced in another that is causing further confusion. On another note, to me, understanding pointers doesn't really tell me about how to utilize a function pointer. I get that a pointer is an address in memory that stores another address in memory that stores a value depending on the type, or more generally reads a certain number of bytes starting at that memory address based on the type it was declared or casted to. I made function pointers in a test program, and it behaves slightly different from an integer pointer. If I have a function pointer called C, and I watch C and star C, they are reported the same. It gives me a memory address, then says the signature of the function in parentheses. If C was an integer pointer, C would return the memory address to the integer, and star C would return the integer value itself. None of this helps me understand implementation. It's like saying f equals the derivative of p with respect to time. Now I should be able to solve every Newtonian mechanics problem. I'm new to C++, C and C++, and I've learned everything I know about it from watching your stream. My degree is in physics, and I started coding with C# 8 years ago for work purposes, so all my experience is based on what I'd call pattern recognition. I found out about Handmade Hero around 2 years after you started, so I've been watching every episode, sometimes more than once, and chugging along on episode 52 currently. I found the Minkowski difference sum fascinating, as I have never seen that application of it. I only know Minkowski from space-time relativity diagrams. I watched your Molly Rocket video from 2006 on Minkowski and GJK algorithms as well. I can't thank you enough for the work you put in streaming and educating. It's the best $15 I've ever spent. Sorry for the long scatterbrained email. I spent several hours running it, and I'm really tired right now. First of all, thank you for writing in. This is very complete and gives me everything I need to understand sort of where your confusions probably are with some of this stuff. Let me first finish my bubble tea here, and I will kind of go into more detail here. Okay. Wait, there's still some tapioca left in my bubble tea. I got to get those out here. Never leave a boba behind. That's my feeling on bubble tea. All right. Okay. So first of all, let me say that I don't think you are alone in your feeling that function pointers and calling functions in general is a little bit impenetrable in terms of understanding how it works in C. It's one of those things that C kind of dances around a little bit and maybe doesn't end up doing a particularly good job at making be orthogonal and logical. Programming languages all have things that they do well and things that they don't do so well, and there are always edge cases and stuff like that. C, I don't think really ever reached maturity with respect to the relationship between code and data. It's just not something that really happened in C. It's a problem, and it does carry forward to today. And not only does it create problems with respect to what we can do in C and what we would like to be able to do in C, but it also creates problems of the form you're experiencing, which is to say that, and actually I would say that I actually disagree with your analogy of f equals dp over dt. Now I should be able to solve every Newtonian mechanics problem. That's actually being more generous to C than it deserves, because f equals dp over dt is actually at least consistent with every Newtonian mechanics problem, and there are no gotchas in there as far as I'm aware. C's function pointer stuff actually is not at all consistent with the way the other pointers to things work in a lot of ways, and so in some sense it's not even as good as saying f equals the derivative position over time, go solve every Newtonian mechanics problem. You're actually at a more severe disadvantage, if you will, in trying to come at C's use of functions and pointers and try to understand them just from understanding how regular pointers work and extrapolating from there. So let me start out with a few basic things that I think we should get straight that have never really been addressed on Handmade Hero very much because they're not really relevant to the way we do development on Handmade Hero. And that really has to do with translation units, what they are, how source code is linked, and so on. I'd like to start with that and then build up to the function pointer part of things as we go. Okay. So let's do some of that. So what I want to point out, and I kind of go back, and this should be probably more familiar to the person who was writing in than probably a lot of the other people who are watching, because the person who's writing in started recently at the beginning of the series. Everyone else maybe has forgotten when we did the video series, but obviously you know that we, in our code, we have a thing called build.bat here. And build.bat is just a batch file that does our build. Now, why do I use a batch file to do our build? Well, the reason I use a batch file to do our build is because, maybe 5-6 years ago or so, I found that build systems took more time to maintain and use than they actually saved in practice, and that most code, even code that's 200,000, 300,000 lines of worth of source, which are the kinds of size projects that I typically deal with, are just not, it's not necessary to use a build tool. Now, when you get into heinous monstrosities that are like libraries on top of libraries on top of libraries on top of libraries on top of Java on top of and scripting on top of JavaScript and like piles and pile, I guess that you couldn't really do that quite that. You can't put mscripted on top of JavaScript, but you know what I mean. If you have these monstrosities that are kind of the way that people build some of these modern projects, which I won't touch the 10-foot pole, then you can understand why people maybe still need to use build systems, because these things take hours potentially to build from scratch. But in our case, where we're talking about a game code base that's written by hand and is relatively clean, these things can be several hundreds of thousands of lines, which is sufficient for any game that I've ever seen. Really, if you're actually being coherent about it, you just don't need them. So that's why I use a build.bat to build it. And the way that I do that is I call a single, or in this case, 2 different calls to the compiler. And in those lines, it implicitly invokes the linker. It's a compile and link command. I only call it twice, and I only produce 2 executable portions. One's an executable and one's a DLL. That is how we build Handmade Hero. Implicit in that is a bunch of stuff that is relevant to the understanding of what a function pointer even is, how they come about, and how you can start to understand things, such as the question that was asked in the email about how one CPP file talks to another. So what I'd like to do is depart just briefly from the build.bat that we were using, so that we can talk about what the compiler actually does, what the linker actually does, look at both of those, and start to talk about what a CPP file even is, what an H file is, and all of those sorts of things, so that you can really get a coherent understanding of exactly what's going on here. And then we'll move up to the code level, the assembly level itself, and watch exactly how these things are working on a number of fronts. Okay, so let me start by making something out here in the temp directory, let's say, or not temp directory, but I'm going to call this, what was the name that was on here? Okay, so I'm going to call this Naker 314. Incidentally, I should mention that if those of you who are with me on the pre-stream know that I was eating a meat pie for lunch, and the place where I got the meat pie is called 314 Pie. So I feel like this is serendipitous in a certain way. So here I am in a clean directory, and what I'm going to do is I'm just going to make a file in here. I don't know what it's going to be, temp.cpp, let's say, or maybe I'll call this main.cpp. And then I'm going to open it in 4Coder. Here it is. I don't actually need that there. But what we're going to do here is I'm going to make something that the C compiler can compile. Right? I'm just going to make a very, very simple thing like you've seen many times before, and I'm not going to decorate it in any way. I'm just going to have a void function here. I'm going to make something where I take an int in, and that's it. Right? And maybe I'll make it a little bit more interesting here by saying that I'm going to generate a result. I'm going to multiply whatever the input is that I receive. I'm going to multiply it by 2. Right? So that's the entirety of what I've created. Right? So we all know intuitively what this is now. Right? We all know intuitively what we're looking at here, but how often do we really talk about, on Handmade Hero, we don't. How often do we really talk about exactly what's going on in here, right? So this main.cpp is just a text file on a drive, right? And it's really crucial to emphasize this point in a certain sense, because there are languages out there where files have more meaning. But in C++, in C and C, it's important to understand that files on a drive literally have no meaning until we invoke the compiler and it sort of is instructed as to how to interpret those files. Files don't have a one-to-one correspondence with anything in particular in C. And so it's important to understand all we have done now, again, it may seem pedantic, but I'm just going to hammer it home. All we have done is type some text into a file, and it has no meaning whatsoever, right? Not yet anyway. OK. So now if I'm out here, I have the ability to invoke a compiler. In my case, it's Microsoft's C compiler, so I type CL. If you were on another platform, maybe you would be typing Clang or CC or something if you were on Linux. Or on Mac OS X or something like this. But point being, I have some way to invoke a compiler. And there's two different ways that I might ask the compiler to deal with this file. One is traditionally called compilation, and the other is traditionally called linking. And we don't super distinguish those two in Handmade Hero, but I want to distinguish them now. So what I'm going to do first is I'm going to take this main.cpp file, right? And I'm just going to call CL on it. And I want you to see what happens, right? So when I just call CL with main.cpp, what you can see here is actually two steps have occurred. The first step is it is invoked the compiler, which you can see here on main.cpp. And what you'll note is there were no errors. Now, I could have had an error, like maybe I accidentally typed Y here, right? Then it would have stopped. It would have invoked the compiler and stopped, OK? But instead, if you take a look at what happens with what I have here, when there's no errors, it then progresses onto a second stage where it's actually invoking the linker. Now, the linker is not CL. The linker is actually a separate command called link, which you can see if I actually type that separately. But what happens is that CL as a command will invoke both the compiler and the linker if told to do nothing else. And that is the way that it's currently working on Handmade Hero, right? So what you'll note here is that you'll see it says entry point must be defined. Now, what is happening? Okay, even just right now, I can already start discussing what is going on in terms of functions and how they work and how text files are related to them and all this sort of stuff. So let's break down exactly what we're seeing here before we even go one step further and actually do define an entry point. Okay. So what has happened here is actually a two-stage process where the first thing that happened is this main.cpp file was fed to the compiler. It started interpreting it because of its extension. There's an automatic detection, right, that occurs here where it's going to look at the extension, it's going to see a .cpp, and Microsoft's compiler will just intuitively treat that as a C++ file, meaning it will start to interpret the text that it sees as if it is C++ text. Okay? That is not an absolute requirement. For example, let's suppose I did something here that was exclusively the domain of C++, right? That does not exist in C. Here's a bunch of things which should not compile in a C program. And when I hit cl main.cpp, you will notice that it does not complain. However, if I look at the command line arguments to the compiler, what I can actually see, and of course there's so many of them now that it's kind of hard to actually find, but if you can manage to find it, you can see that you get information in here that actually tells you what kind of input file the compiler is going to expect. And let me see if I can actually scroll back up to this here and see if I can have some kind of an understanding that it should be doing C compilation and not C++ compilation, which actually maybe I can use less here to help us find that. So here we'll get the help, type it to less, and then let's see if I can get just C as opposed to C++ through here. Let me take a look at this. No, no. There we go. So you can see right here this /tc compile all files as .c, right? And so what I'm going to do here is I'm going to say, /tc, and now I'm going to pass it main.cpp. And what you can see is that now it immediately starts to complain about these constructs here because it doesn't understand what they are. It sees class and assumes, well, that must be something I don't know what it is yet. Then I see this is my class. I'm like, well, I can't have an undeclared identifier followed by another undeclared identifier. Something's wrong. So you're going to have to fix this for me, right? So again, just to be clear on this, there is no real understanding of what a file contains until we tell the compiler what it is looking at. And the compiler in this case is operating very much like a stream processor. It is taking in the text. It expects that text to be compiled to a certain language specification. By default, if that came from a CPP file, it will assume that it is CPP. If we tell it otherwise, it will not make that assumption. If it came from a C file, it would assume it's C. Again, we could override that if we wanted to, right? But it is acting entirely as a stream processor here. And what that means is that I can just do whatever I want in here, and just the text will just get munged together. So for example, if I have another file, as we often do in Handmade Hero, I'm going to copy this to like main2.cpp, let's say, right? What I can do here is I can load main2.cpp and put something else in here, right? Something completely other than that, where I say, int bar, int y, and maybe this has a result, and it is y times y, so it's squared, and I'm going to return that result. In here, if I were to call this, so I were to say, okay, the result is actually that I call bar of 2 times x, like so. You can now see that I'm calling the main2.cpp file from the main.cpp file. If I were to merely call the compilation step on this now, what you will see is that the compiler is taking that text file in, it's doing the compilation on it, it does not see, right? It does not see bar anywhere. So when it gets to the request to call bar, it's like, I don't know what you're talking about, right? Now, there's a number of ways that I can fix that problem. And problem is the wrong thing to say here, because what I'm trying to do is just show how the stream processing works and start to motivate our discussion of functions and how they work. So it's not really a problem, but there's multiple ways I can get bar into the visibility of the compiler in this step. One of them is I could just include the CPP file. Now, again, this may seem counterintuitive, especially to people who are, indoctrinated perhaps to think that the only thing you include are .h files. Not true. C's compiler is simply a stream processor. It does not care where the code comes from. It does not even look at what the files are or what they are called, unless, again, it's to do some kind of auto-detection to override, or I should say auto-detection in the case where you have not specified what language you're using. So it will assume C++ and so on. It's only going to do that on the main file, right? It's only going to do that on the main file. So let me go ahead and motivate this a little further. For example, so let's say in this case, actually, I'm gonna change gears slightly here, back away a little bit from one of the things I just said. I'm gonna, instead of main2.cpp, I'm gonna call it main2.c, right? I would have done this initially if I had thought of it, didn't think of it, right? So I'm gonna go ahead and include main2.c. Okay? And now I'm going to go ahead and do my build again. Right? Now you can see the compilation step works. Okay? Why does the compilation step work? It's because this include, all this directive does is it takes the contents of main2.c and it sticks those contents in the place of the include. It is literally required to do exactly that. So this is not like telling the compiler to import something in the way that other languages might reference a package or a file that has things in it and say, I am going to call things from this, understand that it's a separate file, but I'm going to call things from it. C does not make that distinction. When you do a pound include, it is a direct textual include, and so it has to be considered more like, if you're considering other languages, things that literally import text directly into the stream of compilation, right? So what you'll notice here is that if I went over to main.c, main2.c, right? Go ahead and load that here. Again, just to hammer this home, let's put that class thing in there. right? Let's put that class thing in there. I compile. I don't get any errors if I compile main.cpp, even though main2 is a .c file. Again, the only time that the compiler does auto detection is on the initial file that it is passed. The pound include is not considered a re-examination of any files. It's just taking the file and inserting it verbatim as if you had just cut and pasted it. So it is never going to look at what this name is. The only thing it's going to do is use that to load it from the drive. It's never going to think about what that name is. It's never going to ask if it's a .h or a .c. It's never going to ask if it's a .c or a .cpp. It is literally just a cut and paste. That's all it is. I can prove it to you. If I were to try to compile main2.c, it would auto-detect that it's a .c file and again issue the error because now it's compiling in C mode because the time when that auto-detection happens is on the initial compile, right? When you initially pass that file. Anything that is included in the file, right, is just glommed in. Okay, we can take this a step further and say, well, I actually can pass multiple things on the command line, right? I can tell it in this case that I want to pass main and main2, right? I can ask for both of them. Now here's the part where we really depart from a lot of the stuff we do in Handmade Hero, where we're starting to consider multiple file compilation. Again, in Handmade Hero, because it is much more optimal in terms of compile speed, we compile everything as one big file with just a main base file that pound includes all the other files. Because again, like I said, C doesn't care about files really in any specific sense. The C compiler, all it's intending to do is to take a big old stream of text that it assumes is in either C or C++ form, whichever one you tell it, and turn that into its output. And we're going to talk a lot about the output, so I'm intentionally not going deeper into that, but that's all it's intending to do. It can do that many times, or it can do it one time. So if I want to be most optimal, I'm just going to invoke it once. I'm going to have a main.cpp, which pound includes everything else I want, like the actual code, not H files, but everything I want, H's, CPPs, all the code, into one giant textual glob that the compiler digests all at once and spits out a single result, right? That's for efficiency's sake. But instead, like you see here, I can choose to pass things independently on the command line, and it will compile them in turn. And what you can see happening here is specifically it's actually invoking two separate compilation steps, one for main2.c, one for main.cpp, and the main2c one has errors. The main CPP one does not have any errors other than it does not know what to make of this call to bar, right? Okay. So I'm going to take a second just to let that sink in, okay? Because again, we're departing from the way that Handmade Hero things are built. So let's dive into this sort of idea of a multi-file build so that we can start to understand what that means, right? Now again, I really want to emphasize, a multi-file build really doesn't have anything to do with the concept that there are multiple files. What we're really talking about here is the fact that we're asking the compiler to consider multiple chunks of text independently. We have chosen to break that up such that one of them is one file and one of them is another. But we could easily not do that. And so just to underscore that, I'm going to create one more file, main3.cpp. Oops. All right. I'm going to load that file in. I'm going to have the definition of bar in there, and I'm going to go to main2.c, and the only thing that's going to be in main2.c is my class declaration, okay? Now, what will happen in this case if I try to compile them all together, right? Main2.c, main3.cpp, main.cpp, what we will see is that I get only unfound bar. It doesn't know what to make of bar, right, in my main still. Main3 compiles just fine because it's just the one definition of bar. And main2 still has the problem because it's thinking of main2.c as a C file. So now what I'm going to do is I'm just going to say, okay, in my main.cpp, I'm going to include main2.c, right? I'm going to include that file, and then I'm going to remove it from the command line, right? So now I'm going to say, let's compile these files, and here we go. So what I've done there, again, I'm just trying to underscore the fact that the number of C or CPP files that you have has nothing to do with what the language will actually look at. The language is going to look at what you eventually produce as streams to the compiler. These are called typically translation units. And they're called that instead of files specifically because a single translation unit is actually made up of a file that you launch on the command line like cl main.cpp and all of the files it might include. It could include hundreds of files, it can include no files, it can include H files, C files, CPP files, doesn't matter. No one's going to look at what those files were called, where they are, or anything other than just what their contents were, and those contents are going to be inserted directly into the stream. That is how it's going to work. So just what I've tried to get at here is just the step one, which is to understand the fact that we are going to control, and we are always in control of, what our translation units are. And a translation unit is a set of text passed to the compiler to be considered as a unit. And the way that we do that in most compilers is by specifying individual files on the command line, each of which then comprises a translation unit, by aggregating however many files it has included in it. So #include will pull all sorts of other physical files in to this one translation unit. All right? So when we say cl main3.cpp and main.cpp, we are talking about two separate translation units. One of those translation units is strictly main3.cpp. So in the main3.cpp case, we have one translation unit corresponding with a single file. In the other case of main.cpp, we have one translation unit that is consisting of two separate files, right? It's main.cpp, but also main2.c, which is #included. So again, very important to understand, translation units have nothing to do with how many files you have, because you are in control of how many files will end up being pulled in to that translation unit via the #include directive. So hopefully that's very clear and there's no mystery there. Again, we have not talked anything about how these functions are actually getting built, how they're getting linked, how they're finding each other, any of that stuff. I'm only trying to establish the baseline understanding of what is a translation unit and how do you control it. Okay? All right. So now let's move on to step 2. When I hit return, you'll notice that I do not have a properly completing compilation step even here, specifically for my main.cpp. And the reason that that can't, because remember, it's invoked twice. Here's my two compilation units, right? This one succeeded. It was able to process this translation unit with no issues. When it got to processing this translation unit, main.cpp, it was unable to complete the processing of that translation unit because it could not find bar. Now, why couldn't it find bar, right? And furthermore, what would happen if I was to force this function to be compiled in C form, for example, right? Because I think, I don't know, let me actually see if this is the case. Oh, it's got this #include. So I'm gonna turn this off temporarily just so I can see. Yeah. So I want to I wanted to show you what happens here if I do this compilation. Again, I had to uninclude this because I'm not. This is a C++ construct that we can't have in a C program. When I switched to C and I told it, hey, do main3.cpp and main.cpp, I want you to treat them as C files, not CPP files, right? What you'll notice is the complaint about bar goes away, right? You'll notice I am not getting an error that's complaining about bar. However, when I switch back to compiling a CPP, I do get an error about bar, right? So what's going on there? That takes us to the next stage of sort of the understanding of how translation units work and how multi-file stuff works, right? Which we, again, have to understand before we can get to the understanding of linkage of functions and function pointers. Okay. So the problem here is that in C, in the original C, the way that compilation worked was that when you called a function, remember, there's no such thing as operator overloading in C. That was not a thing that C had. I'm sorry, operator. There was no such thing as function overloading in C. There was also nothing like polymorphic types that had ways of like casting between them automatically, like implicit constructors, all these sorts of things that you see in C++. So the rule in original C was that if the compiler saw a call to a function that it did not recognize, so in this case we have bar, and I'm not even including main.c2.c anymore, so this is the entirety of the translation unit now, is just this int foo. It sees this bar, it's like, you've never told me what bar is. The C compiler would just go, well, it looks like you're passing an int here. I'm going to assume that bar is a function that takes an integer. And we'll deal with it later. I'm just going to create the code that, in this case, would call a function that looked like that. And I'm just going to assume that later on, during linking, which we haven't talked about yet, we'll take care of this, right? C++, on the other hand, tightened up that requirement considerably. What C++ said was, I always need to know what a function is, like what the definition of a function is before you call it. You know, if for no other reason than the fact that, hey, there might be multiple overloaded versions of this function, one that takes an int, one that takes a float, whatever. I don't necessarily know even what you're calling if I haven't been told what all the possible versions of this function are. So it always wants to see the function before it actually accepts the call to the function, right? So it's not, like the C compiler, going to allow me to call a function that I have never told it anything about. Now, one way to solve this, obviously, is to define the entire function. But as you might imagine, especially if the functions call each other, there may be, if I have one function that calls, if foo calls bar, but bar calls foo in some kind of circuitous way, I can't possibly structure it so that they both occur before each other, right? One of the function bodies has to happen first, one of the function bodies has to happen second. So obviously one of the constructs that even C had, because you may want to do so just for your own error checking, but that C++ requires, is that you define, or I should say declare a function before you use it. You do not actually have to define what the function does. You only have to provide what its signature is so that it's clear how it would be called. So in this case, it is sufficient for me to use just the declaration of the function, not its definition over here that includes the body. Just the declaration, which is the same as the preamble to the definition, but that does not have to include the body. That is sufficient to tell the C++ compiler what that function actually is and to allow it to call it, right? Okay, so what I'm going to do is I'm going to include that in here. I'm going to include that function declaration, and now I'm going to try compiling again, right? And now what you can see is we're back to good. We are no longer getting a complaint that bar is not defined because bar that bar is, what did it call it? Undeclared, I believe. Or unrecognized. Identifier not found is all it said, right? Which is true. It doesn't have any idea because it doesn't really even know what it is at that point, right? And so in this case, now we have gotten ourselves back to OK. We now have told the compiler when it is processing the main.cpp translation unit, it now has the information it needs to do compilation, right? OK. So let's get a little bit more aggressive here and move on to the concept of linking, okay? And this starts to get at the central sort of thing that one of the sort of phrases that the person who wrote in asked about, which was how do CPP files talk to each other, right? Because this is kind of an interesting question in the abstract sense. I've got these files. How can they call each other? What's going on? I don't know, right? And then you've got function pointers on top of this, and how do I take a function pointer between two files? Is what's going on, et cetera, right? So taking a look at this, what the point that I kind of want to get across here is that nowhere at all is there any verification that this bar function actually exists anywhere, right? And I can underscore that point by removing bar entirely from the compiler's consideration. Remember, bar is defined in main3.cpp, but I could choose to only compile main, right? Only compiling main.cpp at this point, right? So at that point, when I'm only compiling main, I end up in a situation where now things get pushed to the next step, which is the linking step. And that's the part that I want to look at now. So first of all, what's going on here, right? And we're kind of going to get to it. We're going to ping pong back and talk about object files in a second. You can actually see that they're getting created here, main.obj, main3.obj. We'll talk about what those are in a second. But I want to talk about the linker first and then sort of loop back around. All right. So implicit in everything that we just said, and now we're going to have to actually address it, is what does compilation mean versus linking, right? What does this mean? Why are these two things, what do they even have to do with each other? Maybe you're more familiar with a language that doesn't even have these things. There's no such thing as two distinct steps of processing your code, right? Well, the way that C and C++, and I guess really this comes from C, traditionally handled the concept that compilation, or rather processing of your program, might take a long time, is that it allowed that compilation to be done in sort of parts, right? So if you had a 100,000 line program, which, let's say back in 1970 would have been extraordinary, perhaps in terms of its largeness, in terms of how long that it would take to process this, or even if the compiler would even have enough memory to process it, who knows? I don't want to say that that's the correct size to be large in those days, and obviously it would depend on the machine you were using and so on. But one of the things that was introduced as an optimization in that case was the idea that if you were going to, and introduced in C, this is by no means specific to C, it's not like they invented this idea, this is a common idea, is that there's two phases of work that have to be done in order to translate the textual content of your code into something that the computer can actually execute. The first pass is the compilation pass, traditionally called the compiler. That is responsible for taking the actual code that you've written and turning it into, essentially machine code, right? Assembly language code. But a bunch of the things at that point that need to be known in order to finalize that code are left unfinalized. So for example, in this case here, where I have this function, I have all the information I need in order to produce the machine code for this function self-contained. It's an int, it returns an int, it takes an int, it computes 2 times a value, it calls a function bar, it then takes that result and returns it. I have everything I need to produce the machine code except for one thing, which is the address of the function bar, right? So if you imagine what this code is going to look like, it's going to look like, I'm going to have some machine code that sets up the stack, and then we have a call instruction, and that call instruction is going to have an address of where to call. And it is that address that the compiler does not have yet, because all it's got is a definition, right? Declaration that says, here is the signature, here is how you call bar. So I've given it enough information to know how to generate the machine code to call bar. But I haven't told it what bar is. It has no idea what the address of bar might be, right? None whatsoever. So that is where the second step, the linkage step, comes from. It is the job of the linker, and the linker has grown to encompass other jobs, including code generation sometimes for optimization purposes. But traditionally, it was more about compilation pretty much generates the machine code. Linking just pulls that machine code together and replaces the addresses. But like I said, it's grown over time so that the linker now can do more code gen to do optimization and stuff like this. But the linking phase, its job is to take the output of the compiler, which may be many different sort of pieces. Especially if I have 30 or 40 CPP files, all of which I'm compiling as separate translation units. So however many translation units I have that many outputs. the linker is going to take all of those and it's going to compile them, well, not compile, it's going to link them into the executable that I can actually run. And it's going to do that by looking at all of the names of all of the functions that have been defined, as well as things like global variables, which also have to have addresses associated with them. And it's now going to take that machine code and patch in all of the places where the addresses were previously missing because they weren't known with the actual resolved addresses that says where these things are in the final executable. Okay? So that is what the linker is doing. Now, let's start with what we're seeing as linker output here. I'm asking it to compile main.cpp. So I've removed one of my translation units, main3. But let's say I left main3 in there just for the sake of an argument, and we can see what's going on here. So I call main3.cpp, I call main.cpp. We're getting compilation. The compilation here has succeeded. There's been no errors in the compilation. What does that mean? It means that each of those two translation units, main3.cpp, main.cpp, again, remember, not files, translation units, because one of them includes main2.c. So we actually have 3 files that were involved in compilation, but 2 of them got funneled into one translation unit, 1 of them into the other, right? The compiler did the work of analyzing the source code that was input, and it generated what is called object code, which is compiled like machine instructions basically for doing the work that the source code implied, but it left out the step of fixing up those addresses because they weren't known. Now, if we look at the actual drive, even though we never asked the compiler to do this, it did it automatically because it needs to in order to support the multi-stage compilation. You can see that actually it output for each translation unit, and you see it pairs directly with the translation unit. Main2.c did not get one. Why? It is not a translation unit. Main3.cpp was the translation unit, and main.cpp was the translation unit, and main.cpp included main2.c. So all of the main2.c code, if there was any, went into main.obj, the result of that translation, right? So what we can see here is it wrote out that machine code. Right? Main.obj and main3.obj actually are the results of the compilation step, which did not fail, so it successfully output those 2 obj files. I didn't get an executable because the linker failed, but I did get obj files because the compiler succeeded, right? So now let's take a look here at these. I think I can. I don't know if I can look at these or not. Yes. Okay. It's been a long time since I've done any of these. Can I get? I'm sorry. I'm just going to. Yeah. Okay. Just want to make sure. It's been a long time since I've done this sort of stuff. So, bear with me here. But it turns out it is exactly as I remember it. So. What can we now do to verify that sort of and cement what I'm trying to tell you here, so that you know that I'm not making this up and sort of floating around in the stratosphere telling you ridiculous things? Well, so let's actually take a second to verify that what I'm saying is actually what's going on here, and just to get you familiar with actually how these things work in practice, get your hands dirty, get under the car, so to speak, and like look, I don't know how cars work, so I have no idea. Under the hood, who knows? I don't know how to use cars. I don't even own a car, so who knows? But I imagine this is the kind of thing that people who rebuild their engines know in the car sense. So here we go. There is a utility on the Microsoft compiler, and there's equivalents for your platform as well. If you're not using Microsoft stuff, maybe someone can post in the forums at some point some guides on how to do this if you're on Linux or Mac or and so on. But there is a utility called dumpbin that comes with the Microsoft Visual Studio compiler, which is what we use on Handmade here. And it is a tool whose sole job is to take the output of the compiler or the linker and sort of reverse engineer what its contents are, right? So it's supposed to take it and go, okay, here's an OBJ, here's an executable, whatever. tell me what you can about that by looking at the way that the compiler wrote it out and spit out something human readable, right? It's got a number of ways I can analyze this sort of stuff. The one that I am using right now is called disasm. The disasm switch is basically saying, hey, you produced this OBJ file. I know that an OBJ file is the result of translating some of my source code into machine code that the computer can execute, but with the addresses left unprocessed, right? So what I'd like you to do is give me the disassembly of that machine code. Show me what it is. And so here is that line, dump bin / disasm main.obj. Main.obj is that translation unit that includes, right, this int foo, and in fact, I'm going to go ahead and load it up on this side so that we can see it a little more clearly. So you can look at them both at the same time. So here it is, int foo, int x, int result equals bar 2 times x, and here is the result, okay? Now here is what the compiler produced. It produced a label, right? That's what this is here. And again, this is this OBJ file is essentially sort of a pack file, kind of like the kind that we have in Handmade here for art assets, where it's taken, you know, if we have multiple functions, and you know what, let me just throw one in here. That'll be distinct. The floating point version of foo, right? There we go. So now let's compile, so that you can see two of them. Where's my dump bin? There it is. Okay. So let's take a look at what we got, right? Again, it looks a lot like a pack file. And what we're seeing here, again, is a textual display. The actual binary format of this file, it's telling us right here that it's a COF object. COF, I think, is the common object file format or something like this. I don't even remember what it stands for. Let's find out what it stands for. It stands for something like that. Common object file format, yep. It's basically a binary specification that says, here's how we produce packages that sort of list, here's a bunch of functions and global variable data and so on, that does not quite yet have the addresses bound, right? That's what it specifies. As well as I think it provides maybe debug, ways to include debug data. I don't really know. It's been a long time since I looked at it, but it's got a bunch of that stuff in it, right? So it is a binary file format. Here is a textual listing of what is contained in that file. There's a label which says, here is the function foo, right? And we'll talk about what this is in a second. But here is the function foo. Here is the code for that function foo. Then here is a function called baz, and here is the code for that function, right? And so what you can see here is it's done exactly what we would have expected. It's going to go ahead and have the preamble to the function, right? You can see that it chose to implement the multiply by 2 as a shift left by 1, which is kind of amusing, right? It's already doing some optimizations there. Rather than issuing an imul, it just does an SHL, even though we weren't asking for anything specific, but did that. It's pushing that in to a particular register, right, which is for the call. I believe that the calling convention probably says that that should go in ECX. So what it's doing here is it's setting that up. And I guess maybe I should be a little more clear what happens there, because we haven't talked about that yet. But I just want to finish this, and we can talk a little bit more about that in a second. It's then calling, again, a function that it doesn't know. So you notice there's no address here. You can see a lot of these things have addressy looking things on them. They're hard-coded to locations relative to registers. You can see a lot of this stuff here, stack manipulation and that sort of stuff. This is not that way. This is actually a symbol. The symbol is !bar at YAHH at Z. We'll talk about why it looks like that in a second. But that's the call without a known address. And then it's going to take that value that comes back and put it into the return register, which is EAX. And then it's going to fix up the stack and return, right? We then have a bunch of int3s in the dead zone, which is just there, I believe, to make sure that anyone who jumps to this area accidentally issues a fault. I think this is typically padded so that if this function grows, you have to understand there's incremental stuff. I think it tends to leave padding so that if it wants to expand a function, that it doesn't have to recompile things. It's for incremental linking, stuff like that. I believe that's typically what that's for, but I'm not entirely sure. You'd have to ask about, like, these int3s are not necessary, right? Int3 is a thing that breaks into the debugger. It's an interrupt, and so it's basically just dead. It's dead code. It's code that's never supposed to be executed at all. but it's there presumably as padding. You can then see we have our other function, right? This function here is baz. That's the second one. It's floating point. You can see it does exactly the same stuff. It uses the XMM registers because that's where you do floating point math nowadays. It does a mov to load in whatever the input was. It does a mul to basically multiply 2 times the value in this case. I guess, wait, how exactly are we doing this here? Move SS XMM 0, DROO pointer, it's saving that register, which makes sense. Move SS XMM 0, DROO pointer, real out of 4. So actually what's happening here, it looks like, here is the mul that actually does the 2 times. This, it must have put the constant 2 into this data segment here, which is going to have like 2.0 as a constant, and that's what it's loading out there actually. Then it's going to actually take this and move it into the return register and return, right? So again, I know this is all for a beginner. This is going to be overwhelming to try and understand all the assembly language. I just briefly said what it was so you'd understand. You don't have to quite get familiar with that just yet. All I really want you to pay attention to, again, is these things here. These are labels which say here's some code. Here is a call to a symbol that hasn't been defined. Here's some code. And if there's any other calls. This one doesn't have a call, right? Only that one does. OK, so hopefully you understand what's going on there. Now, what you can see if we dump out main3.obj is we have the corresponding symbol. So this is the obj file produced in the main.cpp translation unit, which again includes main2.c as well. So again, it's not file specific. When it goes to call this function, now imagine what the linker has to do. The linker is trying to produce an executable. Whenever it goes through and pulls all these things together, it's going to look and see that it has an address here. It's looking for something called !bar at yahh@z, right? That's what it is looking for. And you can see that in this other obj file here, it has that symbol, !bar at yahh@z, right? So that's how the linker knows how to connect things up. The code, the actual assembly language code, or machine code, I should say, in the coff file that the compiler executes has names which exactly match the names in other translation units. And the linker's job is to line all those up, assign everybody a position in the file, the executable file that's getting output, and then make all those addresses line up. Replace call, something with just call and then some symbol that we don't know what it is, replace that with an actual call to an actual address, right? OK, so let's go one step further now. Let's really try to start to sort of tie all these things together. What you'll notice, and I think this is the part that I was originally trying to motivate, is that if I call this in either way, right? I can call cl main.cpp or cl main3.cpp and main.cpp. In neither case does it complain about bar being missing. Now that makes sense in this case because I gave it a translation unit that actually has bar in it. And in this case I didn't. Why is in this case it not complaining? Well, what we need to understand is that the linker is under no obligation to complain about a missing symbol if it doesn't need the symbol. So the way Microsoft's linker works is it actually starts at what's called the entry point, and it crawls its way outward from there, pulling in the symbols that it needs based on what the entry point actually calls. This is a good way to do dead code elimination because it means that you're never going to link a function into your executable that nobody ever calls. Because why would you want to link in a function that nobody ever calls, right? That doesn't help you in any way because no one can ever call it. It's just wasted space, right? So what's happening here is a very logical and very understandable process because here is the key. All of these translation units that I have, in any project that I have, all of them can have tons of symbols, and all of those symbols can point to each other and blah, blah, blah. But there's one step that's missing. How do I actually start executing my program, right? Because all of these files and all of these functions, all they're doing is pointing back at each other. Right? There is the operating system, Microsoft Windows, which is actually going to run my program. I'm not linking with its source code, right? So it can't call me. How does it call me, right? And so what you have to understand is the next step of the process, right? Which is that at link time, what's going to happen is we're going to be using knowledge, right? The linker is going to be using knowledge of the platform for which it is exporting an executable. And it's going to utilize a priori knowledge of how that operating system loads executables. So what happens when people make an operating system is they rigorously define how they will load a piece of data off of disk and start execution at it, right? And then it is the linker's job to make sure that it prepares an executable in such a way so that it conforms with that standard, right? Now, what I would like to do for the next step is going to take a little while. So you're going to have to bear with me here as we try to get through it, right? So first what I'll do is I'll show you the not particularly helpful thing that's about to happen, and then we'll sort of go a little bit further. So let's say I actually use the standard for C programs, and I put in here the standard sort of main that you would expect, right? So oops, I didn't mean to do that. So I'm going to go ahead and do a compile now of CL main. And what you can see, if I add this sort of this boilerplate code that is everyone's seen for the how a C file is how execution is supposed to start in a C program, what you can see is that if I do that, I now immediately get the unresolved external symbol error if I'm only compiling that one translation unit that I would have expected to get before. Why am I getting it now? Well, I'm getting it now because I've actually defined a starting point somewhere. And so when I define that actual starting point, the compiler now starts to look at other things that are in that translation unit. Now, it can choose not to look at them because I haven't actually called them, right? So the fact that it's complaining about missing bar referenced function foo is purely advisory, really, because it's under no obligation to even really do that. Because since I haven't called foo, that's not actually necessary. But I'm going to actually call foo here anyway, just to make sure that if you are on a compiler that's even more aggressive, it would work, right? So point being, at some point when we actually start to use this, we will now get our unresolved externals because now it knows that we're actually trying to use these files and these functions and so on. We're starting to actually use the stuff that's in these translation units, right? So that means I do have to have everything defined. But once I have everything defined, what you'll notice is now the linking step actually works, and I get my main3.exe. Why is it called main3.exe? Because that happens to be the first thing that was specified on the command line. The definition of how Microsoft C compiler CL command works is it'll just call it the first thing it saw. It'll call it that.exe. We can control that using like a directive, like the output directive, to tell it to produce some other file, but that's fine by me. And if I want it to be the other way around, I could just switch it like this too, and then the automatic naming would produce a main.exe, right? So I'm going to delete the main3 one and leave it like that. So there's main.exe, right? Again, we have not really covered how all the linking stuff works yet, so we're getting there, but I've just got to take it one step at a time. Okay. Now what you'll notice is some ridiculous stuff has now occurred. Okay, bad things have happened. The train has gone completely off the rails. And how do I know this has happened? And why did I say that we're going to take a bunch of steps? A few minutes ago, you'll notice I said the next thing I want to show you is going to take a lot of steps. You'll have to bear with me. Well, what do you see in front of you right now? What do you see when I take this directory? Well, you can see that main3.obj took 795 bytes to encode as an object file. And main.cpp and main2.c, the other translation unit, took 1,409 bytes to encode, right? Now, I'm no mathematician, as I said at the beginning in the pre-stream, actually, when we were talking about math. But that's just a little over 2K, right? In terms of size. So that's how much machine code we asked the compiler to make. That's how much it took to represent the source code we gave it. So why on earth is it an 80K executable that popped out? Like, what happened here, right? What is going on? It's nuts, right? I mean, stuff has gone completely off the rails. The answer here is a bunch of implicit stuff. A bunch of implicit stuff that the compiler just does, and which we are now going to have to turn all of it off to try to get down to the understanding that I'm trying to give you, which is about exactly what happens. So bear with me as I talk about all the stuff that the compiler just basically pooped on us in a little like poop sauce sundae. All right, so where does this problem come from? Well, it comes from the fact that if you think about what's supposed to happen, if you pop open a copy of Kernighan and Ritchie C or something like this, or the definition of C, is it's supposed to be that if I want to write a C program, I can have int main, int argc, char argv, and the execution of my program will start there, right? That is what's supposed to happen. That's the definition of how a C program is supposed to work. It's in the standard. That's just what happens, right? Well, unfortunately, that has almost nothing to do with how Windows actually runs executables at all. Windows is not defined to conform to the C standard. Windows is its own operating system that has nothing to do with C. And in fact, Pascal was probably a very common thing that Windows was targeting originally, if I remember correctly. In fact, a lot of the really early Windows stuff, I think, was Pascal targeted. But neither here nor there. Point being, Microsoft as an operating system is a program that's running on the computer. It's the thing that needs to load and execute our executable. Again, we'll talk about that a little bit later on when we get to that, when we finally get to that point. But it has no interest in specifying what int main, int argc, char argv has to do with anything, or how you call it, or any of that stuff. So actually what happens is between the specification that Windows lays down for how executables are supposed to run and the actual C specification of how compilation, in how execution of a program is supposed to start. In between there is a giant gulf. And that gulf is filled with code from the C standard library, which Microsoft's compiler, in order to make it appear to be working when you just do int main, int argc, and have the program actually work, which it would in this case, right? That gulf is filled with runtime code that Microsoft's compiler will just plain stick in. Okay? So let's use dump bin just to verify that this is going on again. Remember, I can do disasm like I did before. I can say main.exe and just ask it to give me the disassembly of that code. Now, what you will notice is it is massive, right? All of this code, it just goes on and 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 on. And all of that stuff is based on the fact, again, that Microsoft's compiler interprets your decision to try and compile C code as an implicit request for the C runtime library's preamble stuff that allows you to get to main, for that to be included. And that is all the code that you're seeing scrolling across the screen right now. It is the machine code that you are looking at, which has been included for you, that is all the C runtime library setup stuff and preparation and thread stuff and everything. All that stuff is just getting welded in there for you, right? You can't see it, but that's actually what's happening. And it's actually coming from .lib files, which are files that the compiler has in its lib directory. You can actually see, in fact, if we go back up here, you can see that we've got this lib path here, and there's all these sort of, and lib stuff where we've got these different path variables, right, where Microsoft is going to look at include, and I think include and lib are the two. I think these two here. It's going to look at these for pound include files, automatically look for them. It's also going to look for libs automatically in here, right? And what we can see, if we want to, I believe I can sort of motivate this a little bit better, is you can see, well, OK, if I do this compile, it succeeds. It's getting all this code from somewhere. We can tell that's true because we look at the file. There's all this code in there. Where is it coming from? Well, if I want to, I can look at that set lib. And I see what that says there. If I want to, I could do like old lib equals lib, just get it out of there, and then set lib equal to nothing. So now lib is just clear, right? And I believe now if I do the CL, you'll see what I'm talking about. So now I've done a CL here of main and main3.cpp. And what you'll notice is the link failed this time. Why did the link fail? Well, the reason the link failed is because now it can't find the code that it needed to insert. because we took that environment variable away that it was actually using implicitly. Didn't tell us anything about it, but it was implicitly using that as a search path to look for the C standard libraries.lib file, right? But we don't want any of that now, right? So now you can see if I take away its search path so the compiler doesn't know where to find the libs, it's like, hey, I can't link, my dude. You know, I can't find the C runtime library code, and I need that code. I implicitly link with it. That's how I get to main to main into argc ** argv. So help me out here, right? So the first step that we want to take, because we're trying to investigate this from first principles, is we need to stop the compiler from inserting a bunch of code that it wants to insert into our code, and instead tell the compiler to just produce an executable with only our code, right? As close as possible, just take the object files that we gave you and produce just our code. That's all we want, right? So the first thing that I think we can do here, it's always a bit of an archaeological process to get rid of the default library, but let's go ahead and just try it. We can always look it up. Let's see here. If I can find anything in here, ignore the default CLR. No, that's not what we want. Omit default library name. No. Enable TryGas. No. Off by default. No. Rich debugging information. No. Send report. No. No and no. So unfortunately, in here, we don't have what we want. So we're just going to have to wing it. I believe it's no default lib. So when we actually get this, now we kind of have to start talking about the different stages here, but that's okay because that's exactly what I want to do. So what I want to do now is I want to create basically a new build.bat file where we're actually going to control the compilation a little bit more succinctly here, right? And so what I'll do too is let me just go ahead and let me make a dummy file here, build.bat. There we go. OK. And so this build.bat file, what I'm going to do here is I'm going to sort of motivate this by just showing how to do these steps individually and control each of them individually. So that, again, because that's another thing that I want to get to. So on our way to removing it, here's what I want to do. Previously, we're specifying everything on one line, and I was sort of saying, well, what's happening is producing these OBJ files, and then it's calling the linker. Let's do that manually now, so we can see each individual step and control each individual step, right? So what I want to do in this case is I want to only output the C file. I don't want to link, right? I just want to say take an input translation unit and produce an OBJ from it, right? That's the only thing that I want to do. And I should be able to do that by like there's usually a switch for this. Again, I never remember what these switches are because you do them once and you put them in your batch file and then you forget what they are. So let's see. Let me see if I can here for link. No. There it is. So I thought it was /c, but then I looked at slash lowercase c. So you can see compile only, no link. So if I want to, I can make, in any one of these cases, I can say, oh, compile main .cpp, but what I want you to do is I want you to only produce the OBJ file. So you can see that all it does in this case is produce that one OBJ file. So in fact, if I delete all the OBJs here, right? So all my OBJs are gone. And now I do cl/c main.cpp. You can see that the only thing it did was produce the OBJ. So now we are in a position to actually be able to manually control each step of the process and see it. So we can say, all right, what I want you to do is produce that OBJ. I want you to produce this OBJ, right? And so if I do this and I do a build, it does each of those, right? It produces both OBJs. And now what I can do is I can specify a link line, right? So I'm actually going to invoke the linker myself rather than letting CL do it for me, right? And what I can pass to the link line is my two OBJs. I can say I want you to link those two OBJs. And now we've gotten back, right, to the place we were before, where I'm like, I link these two OBJs, and it's like I can't find my default library because I nuked its lib path. It can't find them, right? It has no idea where they are. OK, so we now know that no default lib can be specified to the linker and to tell it to stop actually providing the C runtime library as something that it's going to link to, right? So now if I do my build, I should get, well, it should do exactly what I expect it to do, which is give me errors based on stuff that it doesn't know how to do because it doesn't have the C runtime library anymore, right? And that's OK. So now we're down to a situation where we only have to deal with our own code. But we have some issues. So the first thing I'm going to do is I'm going to eliminate our floating point code because there's this thing called float used, which is a way, I don't really want to get into what this is right now. This is a separate issue that has to do with just removing the C runtime library. Basically what it is it's a way of the C runtime library, the way for the compiler to signal that floating point operations were used in the course of compilation. It has nothing to do with the stuff that we're talking about now. It's really better left for the subject of how to compile without the C runtime library, which is not what I want to get into. So all I'm going to do is just leave that out for now and focus just on the parts we actually care about, right? Because if you don't use floating point, you don't have that problem. So we can talk about that on some other stream. So what you can see now is we've got our build working, and I also wonder if I can maybe quiet down the compiler a little bit here in the case it keeps doing our this sort of overly aggressive preamble of printing out the stuff. And I think you kind of all get the point by now. And let's see, quiet. No. Let's see. How do I get you to stop printing out the version? Doesn't look like I know that I can. You know what? Let's take a look quickly at the build.bat and Handmade hero, because I know that I looked this up before. No logo, that's what we're looking for. All right. So I'm also going to stick no logo in there. I guess I'll also use this format. Well, I'll use the slash. That's really the more Windows command line way to do things. All right. OK. So here we can see the steps occurring. Here's the main.cpp compilation. Here's the main3.cpp compilation, which, again, this main.cpp one includes main2. So this is the translation unit. Another translation unit, those two. Now we have the link line. It can't find main CRT startup. And now we're at the part that I actually wanted to talk about next, which, again, is that executable loading and running part of things. OK? So what Windows is going to do is it is going to, it's the thing that runs the code, right? It's the thing that's running on the operating system that you booted into. It's the code that's running right now. So in order to load and run an executable, what it has to do first is it has to map that executable into memory somehow, which, again, we don't really care how. That's not really the point of this particular investigation. So we just care that it gets it into memory somehow, which it will. And then it needs to know where to start, right? It needs to know, how do I start executing the code in this executable, right? It needs a place. And so what's going to happen with the linker is the Windows executable file format, right? Because Windows, again, defines the file format for an exe, how the code's laid out and stuff. That Windows exe file format contains in it information about how to know where to start. So what's going to happen is Windows is going to load the executable. It's going to look at the information that's in the executable that Windows specifically defined to be in there. It's going to pull out of that table, where am I supposed to start? And it's going to point the execution pointer of the processor at that line of code and go, right? That's what's going to happen. So what that means is the linker has to be able to produce that part of the code, which says, here is that part of the executable, which says, here's the address, here's the location in the executable that you're supposed to start at, Windows, so start there. And the convention that they've used for that is to say, well, main CRT startup is the name we will look for if we are not told otherwise in order to start up, right? And what you can see, hopefully somewhere here, let's see, is the function signature for it, although I don't actually see the function signature for it. Can you please, MSDN, tell me I just want to see the function signature. But of course it doesn't seem to tell me. I just want the function signature. Just want the function signature. Well, all right. Oh, Windows. Well, I don't know where the function signature for this is, but I don't really care because I can easily find out, right? All I really have to do if I want the function signature is I can just look at what the C runtime library defines as the function signature, and I can go from there. So let's take a look at where's our simple. We have like a test project, right? Here it is. There we go. So here's this is a test project that we had in Handmade Hero. I'm just going to look at main CRT startup. What is it called? And see if we can find it. Probably I would have to change the type of project in this case. I guess I might have to even do a new one. Let's see here. Actually, you know what I could do too? I could just search for that in the C runtime library. So if I go through here and say, yeah, I don't need that folder. If I just say, all right, in program files, wherever this stuff ended up, let's see. Look in here, Visual Studio, runtime library. So this is the source directory for the runtime library. I'm just going to say, tell me where that is. All right. So now, in theory, I should be able to find this, what the function signature for main CRT startup is. I just want positive confirmation of what it expects that thing to look like. And of course, we could just blindly guess. But let's see. So here's main CRT startup. And it looks like it just does nothing, right? It looks like there's no function signature. There are no parameters passed to it, right? That's what it looks like. So I'm going to go with that for now, because we have a bunch of other stuff to talk about. OK. So here is our function signature. I assume, although it doesn't say what it returns as well, let's actually take a look at that here. Tmain CRT startup. Let me take a look and see what it actually returns. Tmain CRT startup. It returns an integer. So I'm going to return an integer as well. Main CRT startup. OK. OK. So what we've done now is we've just conformed to the standard, or we haven't quite conformed to standard, but we're close to conforming to the standard. I'll show you there's one more thing involved here. We've conformed to the standard of what the linker is looking for as the default entry point to the program, which it's going to look for by name in the OBJs that it gets on the link line. It's going to look for a main CRT startup function defined, and if it finds one, it will use that as the thing it puts in the executable that tells Windows, here is where execution will start. Right? Now, unfortunately for us, that's really not going to quite comply, and that gets into the part of the OBJs that I sort of said we're going to talk about in a second. And so now is the time that we'll talk about it. So if I actually call the build here, what you can see is it still says that the entry point must be defined, and it's like, well, I thought we defined the entry point. I don't understand. Like, what's going on here, right? Something weird is happening. Well, the problem that we run into if we look at what's defined in our file is if we look at these entry points, we've got our two OBJs. Let's take a look at what are ostensibly the thing that defined main CRT startup, what it actually contained in the main.obj, right? Here's the disassembly for it. Now what you'll notice is actually the symbol main CRT startup has not been defined anywhere. The symbol we defined was question mark main CRT startup at YAHXZ, right? So now we have to ask the question, how do we define an actual symbol main CRT startup, and why the heck what is this, right? I glossed over it before. What is this? So now let's talk about what that is. This is called C++ name mangling, colloquially. And what this is remember early on I sort of said, well, in C we didn't have function overloading. Well, C++ does have function overloading. And what that means is that since C never allowed you to have more than one function with the same name, its linker was set up to just say, here's the name of a function, and you call that function by name. I can bind those two together. But when C++ came along, that was no longer sufficient. I can have many different versions of the same function foo, one that takes an integer, one that takes two char stars, one that takes a float, one that takes a struct, one that takes this, right? So what C++ did to continue backwards compatibility with existing C linkers was to just mangle the names of functions so that the name of the function included markup that told you what its function signature was. So this right here is a way of saying that it takes an integer, right? This right here is a way of saying it takes a void. And that's what that name mangling does. What that means is that if an external program is trying to look at an OBJ file and find a specific name, if that name is compiled with C++ name mangling, it will not be found, because the name that it will actually be put under is some mangled name that includes a bunch of stuff from the calling convention and the type specification and all this other stuff. Right? So what we need to do is let the compiler know, not the linker, but the compiler, that this particular function needs to be compiled compliant with the C rules. And there's two ways we can do that. One is we can put it in an extern C block, which tells it to just use that, right? And you can see what happens now when I do it, right? There's my main CRT startup. The other way is we can tell it to do that just as a property of the function name itself, which I believe is just that, right? Nope. Oh, I know. No, sorry. It's still extern C. That's just the calling convention. It's that, right? And now we've actually got a main CRT startup that is actually defined directly in the code, right? OK. So now we're in a good position to actually try to get these two things to connect up. And again, the only problem that we're going to face here is the inability to find the correct, what this should be correctly defined as. And I don't actually know, because again, I couldn't actually find that specifically. So let's just double check here. When I tell it we don't want that, you notice we're getting an entry point must be defined error now, as opposed to a main CRT startup is not defined. So in that particular, let me go ahead in here and just take a look here. We should find, I think we need one additional thing here for our entry point is not defined, because I just want to, again, this is sort of a compiler linker sort of snafu here. I believe if we did this, and let's see here, /link, no default lib. How do I do the? I never under. This is the part that always slows everything down, because you got to remember all the vagaries of this particular compiler's fun. It's /lowercase_link. /lowercase_link, no default lib. There we go. OK. So Again, at this point, now we're in the position of I just want to make sure that this was all happening correctly here. So now we have to figure out how we're going to get the compiler to, the linker to recognize this as the entry point, which means that the entry point has to match exactly. It has to be named the right thing, and it has to take the right variables as well. So now we have to figure out how exactly we're going to do that. And there's two parts to this. So the first part is, again, lining up the thing correctly, but the other part is which thing it's actually looking for. So on Windows, there's two separate ways that it might look for the startup of the start of the code. The first way is if you're trying to build an actual Windows application, where it actually opens Windows and stuff like this. The second way is if you're building a console application. And the linker actually has to specify which of these two things you're doing in the actual executable itself, and Windows will load them differently based on which one you specify. This is why, I don't know if you've ever noticed this is a common complaint of programmers, and Microsoft has never fixed it to the best of my knowledge, unless they finally did in Windows 10, I don't know. I'm not very familiar with Windows 10. But, at least up through Windows 7, there is no way to make an application which, when launched from an icon in Windows, in the shell, in the graphical user interface, does not pop up a console window. And also, when run from a console window, is able to output text to that console window via standard out. There is no way to do it. The reason is because this actually occurs in the actual executable as a thing that Windows will do differently depending on which one you have. If you specify that you are a console application, then when you are run from the GUI, you will get a console window. It will create one, and you'll have it. If you don't specify that, and you're run from the console, you will not get standard out. And there's nothing you can do about it. So people have tried to fake it by finding your console window and hiding it so you don't ever see the fact that it got created and stuff like this. So they try to approximate it, but there is no way to really do it for real, unfortunately. All right. So moving on from that, how is that specified, right? Which kind of these which of these two things are we going to have? Well, there's basically a thing called subsystem. It's a switch to the linker, and it tells it what to put in the executable to make that happen. So you can see right here, here's the subsystems that are supported. In our case, we only care about the ones for app level stuff, which is console, Windows, potentially POSIX. We don't care about things like EFI applications or boot applications, things that are specific to hardware stuff. And in our case, we could do Windows or console. So what we could do here is say, well, subsystem maybe is Windows, right? Maybe we want to make a regular Windows application, let's say. That's what Handmade Hero does. And so let's see what happens when we do a build. And what you can see is it now thinks that there's an unresolved external symbol winmain CRT startup, right? That's what it's looking for if we tell it that's the subsystem. If I switch the subsystem to console, now it's actually works, right? Why does it actually work? Well, it actually works because now it knows what the default entry point should be. And that default entry point is main CRT startup. If we hadn't have defined this, right, it would complain about that instead. So we need that subsystem line in there to tell it which sort of startup code we wanted, right, which kind of executable to mark us as. And then we need to define the corresponding startup. But now that we've defined all of that, we will actually get a working executable. And lo and behold, our working executable is now 1/40th the size that it was when it was shoving the C runtime library in that we didn't want. And if we now look at what this looks like under disassembly, it's quite proper, right? You can see here that this is our entire executable. This is the entire package, the entire executable package of it. You can see here that we've got three separate sort of functions, if you will. And I want to kind of put these side by side so you can see how they work and how that translation occurred. So what I'm going to do is I'm going to dump bin our executable. I'm going to dump bin that executable out to main exe .asm. And then I'm going to dump our OBJs. So our main obj I'm going to disassemble that out, and then I'm going to also do our other translation unit out as well. So here is the main3 obj.asm. Okay? And so now what I'm going to do is I'm going to load those up so you can see them. So here I'm going to load, excuse me. Here I'm going to load in all of those ASM files. So here is the executables ASM file. And you can see, again, this is all of the information here. That's all of the code that's in there. And then I'm going to load in here the main obj.asm file. And here it is, right? And I'm going to look at that. And then I'm also going to load in that main3 obj.asm. So let's start with bar, right? Here you can see the code for bar, and it's pretty obvious where this ended up in our executable. So if we take a look down here, you can see that this code is pretty much occurs verbatim, right? Here's the RSP +8. Here's the RSP 18H, right? Here's the two RSP 20Hs. Here's the dword pointer part. Here's the EAX. Here's the RSP 18H. Here's the ret. Now, that code exists verbatim. Now, why does that code exist verbatim? Again, it has no unresolved symbols. So the only thing the linker had to do when it saw this code, it just had to find a place to put it in the executable. And here is where it put it, right? So this is in our executable where it stuck the actual code, right? That's just where it put it. So now let's flip over to main, which has the rest of our ASM, and take a look at what happened there. Here's our main CRT startup. We start up with an RSP28H. You can see that that code is right here. And now here's where things start to get interesting. Notice what happened to the call. Here is the call, right? This is an instruction to the processor to branch away to a separate piece of the code to execute it and then come back. This call is called to !foo add yah at z, right? And remember, that is this code up here. Right? That is what that code is. Right? It's calling this code. So it is going to have to put that code into the executable somewhere. And you can see that it did exactly that. It put that code right here. And so when the linker smushed these together and put the executable together into one piece, you can see what it did is it replaced this symbol name, which is not useful to the processor because CPUs have no idea what symbols are. They don't care. They just want to see addresses. It provided the address in the executable where that code could be found. And that is where this code went. You can also see that when this code wanted to call bar, again, a symbol that was not known at the time of compilation, it replaced it with the address of the code that was in a different compilation unit, remember, which is right here. Okay? So hopefully now you can see the complete process of assembly that goes from compilation, where you take translation units, which are some collection of files, doesn't matter what they are, some collection of files that can be interpreted as C code or C++ code, go from that source code to an OBJ file. This is what an OBJ file looks like. It's object code. It's basically like machine instructions where a bunch of things have been left undetermined and just have names in their places, right? It then all of those object files are then synthesized together to produce a single executable, which can be loaded by the operating system. That executable has all of the addresses resolved internally, right? Okay? So hopefully everyone is comfortable with what's happening there. Now there's a bunch of stuff in here that you probably don't understand very well. All of this preamble code and stuff like this is maybe very unfamiliar to you because you don't program in assembly language, you don't know what it is. Hey, no surprise there, I don't program in assembly language either. So, again, it's definitely not the sort of thing that we're used to reading. But we're going to have to get a little bit more familiar with it to complete the cycle here. Hopefully, everyone's on board with this so far. Hopefully, nothing that I've said so far is super mysterious. Now that we've gone through every step of the process, you can see how compilation goes from text files on your hard drive to object code to an executable. Now we just have to talk about what actually happens when that executable is actually run. And how it might be partitioned into multiple pieces that can get dynamically linked so that we can finish answering the questions posed by the email that I originally received. Again, most of those questions we can now answer that we actually can look at exactly what's happening in the code and understand literally what's going on, not in some figurative kind of language way that is detached from reality. We can actually look at the reality of what's happening in the processor. Okay. So now let's get to function pointers, right? let's get to actual function pointers, because that is the place that we kind of started this discussion from, where what we wanted to discuss, and all of this stuff was kind of necessary to discuss those things. We have two separate ways that we need to talk about function pointers because one of them is completely dynamic and one of them is slightly less so, right? And so we need to talk about those in a little bit more detail. The first one we need to talk about is just function pointers inside regular code. And that's the one we'll do first because it's the easiest to talk about because we don't need to start involving Windows in our business. The second one is the one that's a little more advanced, which is what happens when we're actually dealing with multiple executable sort of entities like exes, DLLs, Windows system libraries itself, those sorts of things. What happens at that point when we're talking about different executable modules essentially calling each other at runtime? What's happening there? Right? So let's leave that for the second part of the inquiry, and we'll just focus on what happens in an individual program, what goes on when we're actually calling functions, right, by a pointer. OK. So hopefully at this point, everyone is comfortable with what happens when you call things not by a function pointer, right? When you're just calling things by a function name in C, you have seen exactly what happens. So there is no mystery anymore. It just puts the symbol into the object file, and then later the linker resolves that symbol to a hard-coded address that is related to where it is in the executable. Now, there is a little bit of hand-waving there because when that executable is loaded into memory, this address is relative to where the executable was loaded. So it is worth noting that there is a little bit of fun there where either the processor itself has to have the understanding of a relative call, where when you load in an executable, you can call relative to the location, so it doesn't matter where in memory you loaded it, or the executable has to always be loaded at a known base address so that the hard-coded addresses are the actual addresses that are in memory. Or when the executable is loaded, it has to patch the call sites so that all of the call sites that are absolute are shifted based on the loaded base address of the executable, and that requires a fix-up table. That requires that the executable have in it a fix-up table that says where they all are, right? So there is actually a step that you have to consider that is about how those addresses are translated to actual memory addresses later, but you can understand how there's many ways that that could be approached depending on the option. That's operating system and CPU dependent how those will work, right? But you can understand the compilation process now. Pointers are taken out of the equation to a certain extent, and we're literally hard coding addresses where we're just like, this is the location to jump to now, right, for this call. So what happens? What we want to investigate now is what happens in code when we stop talking about a jump to a specific function and we start talking about a jump to a pointer, which could be pointing to any number of functions potentially. All right, so let's get started. Going back to, actually, I guess I'm already in my text editor. I'm used to seeing this. I'm in the debugger. I'm like, I must be in the debugger. No, you're not in the debugger. You're looking at disassembly files. If I come back here to my main.cbp, right, my translation unit here, what I want to do now is I want to start looking at the potential for what I can do with function pointers, right? And so what I want to do is I want to have the ability to call more than one function or something like this. And so I want to start talking about what happens in the compiler when I have these function pointers. So the first thing I need to do is be able to take the address of a function. But you know what? I don't really even need to do very much to do that, right? If I want to, I could say, let's create a void star, right? Because here I got my call to foo, right? Let's create a void star. I'm going to call that void star function pointer, right? And I'm going to take, as the value of function pointer, I'm just going to take foo, right? That's what I'm going to do. And I want to compile it. Now, what you'll notice is that actually worked. Right? There was no errors involved there. That actually worked. And if I want to, I can take a look at what the disassembly is of that particular module now. Here it is. And what you can see happening is literally that exact operation is occurring, right? So let's take a look at what's going on here. Here is the call to foo, right? And what you'll notice is that call to foo is using the symbol. Remember, right? It doesn't know where that is yet. It's using the symbol for foo. Now, granted, when I say it doesn't know where that is yet, it does know about foo because foo is defined in this translation unit. What it doesn't know is where the linker is going to put foo, right? Because the linker is allowed to move this around and put it anywhere it wants in the ending executable. So it can't put in a hard-coded address here because it doesn't know where it's going to put it, right? So it just puts in the symbol and says, hey, Mr. Linker, when you decide where you're going to put foo, go ahead and patch in that address here because I need to call it, right? What you can see happening immediately after that is the LEA instruction, which is a load basically, is going to move to RAX. There's a register in the processor. It's going to move in that same address. So exactly where it was going to call, it's going to move in that address to RAX, right? And then it's going to turn around and store that to RSP plus 20H. Now, RSP is the stack pointer. So RSP plus 20H is just the location of this function pointer star, right? It doesn't appear in here by name because it's a symbol that nobody is referring to, right? The compiler in general doesn't output names to the linker that would just be extraneous. So if nobody ever needs to refer to function pointer outside the scope of the function that's being compiled, they don't get names. In the debug information, they'll get names because the debugger needs to be able to inspect by those names, but the linker doesn't need to see any of that other than in the debug info, right? So that's just not placed in there. Now what we could see, though, is if we moved this function out to a global variable, now it does have a name, right? It does have a name because people can refer to that global variable, right? If I was to do that now, and I may need to decorate that a little bit to make sure, but I don't think so, yeah. If we were to do that now, it becomes even more explicit. Now you can see what it's saying to the linker is, hey, call this function foo. I don't know where it's going to end up. Just make sure wherever you put it, you're going to tell me what the address is. OK, that's this line here, right? Then I've got, OK, go load that address. You know what? Put that in a register. Then store the contents of that. So whatever this address is that's now in RAX, store that out to this global variable, function pointer, blah, 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 right? I don't know where that's going to be because, again, the linker is free to decide where the global variables go when it's defining the sort of the layout of the running executable. But wherever that's going to be, that's where you need to put it, right? So you can see now function pointers in this initial sense are no different than any other pointer in this initial sense. All that's going to happen when you refer to a function by its name in a context where it needs to know that address as if it was a pointer is you will literally just get the pointer. It's just a pointer like any other pointer, right? It points to some memory. That memory happens to be in the mapped memory where the executable code itself resides, and off you go, right? So that is exactly what will happen in this case. And so in that way, a function pointer is no different than any other pointer. It's the same as an int pointer. It's the same as anything else. And one of the things that the person who wrote the email referred to was the fact that it was confusing when he looked in the debugger. He found that he was not actually able to inspect the value of the function pointer, and in that way it was different than integer. That is strictly a function of the fact that the debugger is not showing you it, right? Actually, you could do that. You can dereference a function pointer and see what's actually there. Let's prove it, right? Let's prove that it's no different. Now what I'm going to do is I'm going to load this code, okay? And I need to do a little bit first because we're going to need debug info. So I'm going to go here to build.bat, and I'm going to try and get some debug info here. I believe /zi is the thing that would direct it to produce debug info for us, but I'm not entirely sure, so I'm just going to hope that that's the case. Let's take a look at that main.obj. Again, you can see this code here is the main.obj. I'm going to invoke Developer Studio here on our main.exe and hope that I have some debug information. Again, I don't know that I do. We'll see. I might need to tell the linker about it. So I don't actually have the debug info. Well, you know what, though? Why do we care? We're looking at the assembly. I don't even care. I don't even need to produce the debug info. Forget it. Doesn't matter. It's not important. All right. So here we are at the start of our code. I'm in the debugger. We're at the start of our code. And by now, even though you probably don't know assembly language, maybe you have no idea what assembly language is at all, really, but you can sort of see from what I'm talking about, you at least have the pattern matching, as I think the person originally wrote in called it. You have the pattern matching to know this is the code, right? We're looking at it right here. Here's the code. Even if I have no idea what these things mean, I can see it's the same code, right? And the only difference is the place where foo was actually talked about, right? Here it is, right? It's been inserted, that address has been inserted in place of the symbol foo. I've had the address, right? And so what I want to sort of underscore here, so a couple things we can look at that are pretty interesting, actually. Let me make a brief digression here, just to point out, here's my main.exe. And one of the things that you'll note about this main.exe is you can see that actually the thing that I was talking about before, that relative addressing, is kicking in here where it's been relocated. You can see that the actual addresses where we have been loaded are not the addresses that were filled in here, right? It's slightly different, right? You can see this is 13FFF. It's not 1400 or whatever, right? It is not the same addresses. Let's load this one more time, right? Notice anything suspicious? I'm going to load this many times. You see what's happening here, right? These addresses change every run of the program. Why do these addresses change every run of the program? Well, there's a thing in Windows, address space layout randomization. There we go. ASLR, address space layout randomization, is a technique that is designed to try to improve security on your computer, basically by making sure that hackers can't know the locations of things in executables when they are running. So if you imagine what would happen, right? And this is true of all older operating systems for the most part, then Windows and a bunch of and Linux and stuff, they start implementing address space layout randomization as a sort of exploit mitigation tool. Originally, it was generally the case that most of the time, if you loaded an executable, you were going to get it loading at the same place it always loads. Like an executable just loads at a particular location. And the executable might even have been optimized to load at that location by having all of the addresses hard-coded into it or something like this, right? Without even a fix-up table to fix them. Or maybe all the call instructions were relative. So it didn't have to hard-code addresses. It just hard-coded offsets, and so at that point it was fine. Who knows, right? Well, what ends up happening in here with address space layout randomization is every time Windows loads your executable, it picks a new location in memory to load it at. Because remember, virtual memory is such that Windows pretty much picks your address range for you. It can just say, here's where in the virtual address space your executable is going to be loaded. You have potentially no say in that, so it can move it all around, right? And so every time we run, we get different addresses. So really the only thing that we know is that the actual effective address of all of our functions will be filled in all of the places, either by patching or because they were relative. The instructions were encoded to be relative calls. This is, like I said, some processors support relative branching of certain sizes, some don't. It has to be added, blah, 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 blah. Regardless of what that mechanism is, all we know is that we'll actually get the address of wherever it is in this run of the program that may not be the same location in every run of the program because of address space layout randomization. Okay. So what we can see here when we're coming through, here is the code. We know exactly what code that is. Like I said, it's kind of cool. We don't need the debug information because we just know what code we're looking at. We're looking at this code right here, right? And so what we can see when we step through this code is the processor is doing exactly what I said it was going to do. It's taking the address of the function foo, right, which has been filled in this place right here. And you can see it loading it into the RAX register. If I look at the registers, here's RAX. It's a 64-bit register. It's going to load that in, and lo and behold, there is the address of foo right there. And now it's going to move it out to the stack at this location, right? It's going to move RAX to, I'm sorry, not to the stack. It's going to move it to our global variable, which is this right here. Remember, I switched it. I almost forgot that I switched it. Oops. To this global variable function pointer, right? And so I'm going to go do that. And so now at that memory location, there is now a pointer that's holding that address, that RAX address. That's what's happening, right? Now, what I wanted to show you is you were saying that, oh, this pointer seems different than an int pointer. That's strictly because the debugger doesn't know how to show you a function. If you dereference an integer, it knows how to show you the integer. The debugger, for whatever reason, in the watch window doesn't think to show you disassembly. That's what it should do, right? It should show you the instruction at that point. If you try to dereference a function pointer, it should show you the function, the first line of code potentially at that point, right? But I can prove to you that they're still the same kind of function pointer because let's see exactly what happens. Here's the address, right? This is the address right here. I'm going to look in a memory window, and I'm going to paste that address in, right? And here we go. This is, I'm sorry, I picked the wrong one. That's the address of our function pointer. This is the actual address that was loaded into the function pointer, which is the one that we want to look at, right? So this is where that function pointer is actually pointing, right? It's pointing here. And we know that this should be the contents of foo, right? And if we take a look back at our disassembly, where is our foo? Let's see, dump bin disasm. It should be the one up at the top there, but I just want to make sure that we've got it. Here it is. This is what foo is supposed to look like, right? It's supposed to look like, you know, this instruction, this instruction, this instruction, this instruction, right? So is our function pointer that we just snapped, is it actually pointing to this? Is it just pointing to this memory? Which is, like I said, it should be exactly like an integer pointer. It should just be pointing at some memory, and the contents of that memory should be a bunch of bytes that encode the function. Well, how would we know if that was the case? Well, it just so happens that disassemblies, helpfully, include the code bytes in the corner. These are the bytes, 894C2408, that encode this move instruction. That is the Intel x64, well, I guess I should say AMD x64 since they define the x64 standard, but it's partially the x86 standard. Obviously, it's the extended x86 instruction set for 64-bit. So it's AMD Intel, you might say. Those are the code bytes that correspond to this move instruction. These are the code bytes that correspond to this move instruction. Blah, 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 all the way down to here where we haven't really encoded the bytes because we don't know what we should put here. We know what the symbol is, but we don't yet know what the bytes are. So we would expect them to differ right here because instead of having a symbol fix-up, what we would expect to see here is the actual address. So is that what we have? 894C2408, 894C2408, 4883EC38, 48, right, blah, 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 all the way down to the 8BC8E8. Where are we? 8BC8E8, right? And now, instead of all zeros, what we expect to see is the actual address of something to call. And we do, 4B0000889, blah, 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 right? So again, function pointer, as far as C is concerned, is the same as any other pointer in terms of what the processor is actually going to do with that piece of memory, right? Whenever you're referring to a function pointer, it's just a piece of memory that will store an address. That address is the first byte of the code encoding in x64 machine code of the stuff to do, right? And we can even take this one step further just to make sure that let's just go nuts, just in case you don't believe anything that I've said and you can't really tie it back. If you're just like, I don't know what you're talking about. Like, I don't get it. I just don't understand, right? Let's just make this 100% explicit just how interchangeable these things are, okay? So now what I'm going to do is I'm going to back up a little bit. Hopefully all the stuff about translation units and all that sort of stuff has sunk in. I'm just going to stop mentioning that stuff anymore. And we're just going to work in this one file, right? And I suppose I should have left that include in because we got rid of it there. My bad. So I suppose what I can do here is just say, let's sort of clean this away now, right? And let's make something a little bit more straightforward. So what I'm going to do here is I'm just going to have, just in our one translation unit, I'm going to put two different things in here, right? So I'll leave that stuff in place so that we can talk about it later if we want to, but I'm going to create a very simple thing. So what I'm going to do is I'm going to create a piece of code here that will produce some value. And let me figure out how I want to make this work in the sanest way possible. So here's what I'm going to do. I'm going to create a piece of code that just returns a constant value. That's it, right? That's all it does. I'm going to call it 5. And the only piece of code in 5 is return 5. That's it, right? Then what I'm going to do is I'm going to have a global integer here. I'm going to have a global integer, and I'm going to have a global integer called number. I'm going to delete this for now. And I'm going to set number. In fact, I guess I don't really need it to be global. I'll leave it global. Equal to the result of calling 5. That's what I'm going to do. Right? Simple enough. And now I'm going to step into that code. And here we are. Well, this is the entirety of our program. It's not particularly exciting, is it? All we're doing, set up the stack frame initially. Again, this sub RSP that you see all over the place, all that's doing is giving yourself 28 hex, so OX28 worth of stack space. You're just moving the stack pointer down by that much. It's not relevant to what we're doing right now. It's stack frame stuff we haven't really talked about yet, and I don't know that we really want to get into that yet. Then we're going to call this function, right? And that function is 5. And we can, again, let's just so everyone can see it, let's do the disasm again. Here's the disasm. You can see our startup code, again, sets up that stack frame. It calls the 5 function. Here is the 5 function up there. We're going to do our mov, right? And our mov is going to take whatever 5 returned. And again, the reason that this is the return of 5 here is because the definition in x64, what's called the ABI, or Application Binary Interface, it's the way that function signatures are expected to work. The return value, if it will fit in RAX, EAX, that is where it goes. It stays in a register. So it doesn't put it on the stack. The return value just comes back in a register. So what's going to happen is we're going to call 5. We're expecting 5 to put 5 into a register. We're expecting it to put it in EAX. So when it comes back, we're going to copy whatever it was, that return 5. Right? We're going to put it into number 3HA here, which is that global variable. We're going to move it in there. Okay? That's all we're doing. Hopefully everyone's on board with that. Here we go. Set up the stack frame. We're going to call. Here's our function. That's the function. It just puts 5 in EAX and returns. That's all it does, right? So there we go. Put 5 in EAX, return. And now we're going to move the result in EAX. And we can see in the registers, there's EAX. EAX is the bottom half of RAX. EAX is the 32-bit register name. The way Intel registers work is you have 16-bit, 32-bit, 64-bit sort of registers, they grow. So if I want to, and I think you can even refer to byte, so it's got like each individual one of them. So if I want to refer to just the bottom half, in this case an int is 32 bits, EAX is what it's called. If I wanted to, I can even ask it for that in the watch window, and you can see it returns the bottom half of that, right, and it's fine. So anyway, we're putting that into RAX. You can see that there in the bottom half. There's the 5 that we moved in there, right? It's all good. And then we're going to move that out to this global variable here, which is that global variable. And I can watch that global variable. Even without debug info, I can just tell it, hey, by the way, that's an integer, right, at that location. So why don't you go ahead and, why can't I paste? Cut, paste. There we go. So I can just go ahead and say, by the way, that's an integer. And if we look at what's in the integer, you'll notice at startup, it's nothing, right? But after I execute this mov instruction, it has moved that 5 in there. And so now we have correctly put 5 in there, which is what we'd expect. All right. That is all. Hopefully, everything that we've said today, all of the work we've done today should lead up to this point. You should be completely comfortable with what happened there, except for this one sub-stack bit here, because we haven't talked about the stack. But hopefully this part, the call, right? The getting the 5 value, putting there, should not be very mysterious at this point, right? OK. So just to prove to you that the function pointer is literally just that, it's just that function pointer, now we will go ahead and actually do some shenanigans with it so you can see that it really is just a pointer to a block of memory. OK. So what do we need to do first? Well, implicit in all of this, as you can see, is the fact that C needs to understand how to call a function. And there's a lot of aspects to how to call a function. The first aspect you've seen, and it's the only one we're dealing with here because I wanted to keep it simple, is where does the return value end up and what is that return value, right? In this case, it's just an integer, so it knows that the return value would go in EAX. How does it know that? It knows it because of the ABI. right? And an ABI, application binary interface, an ABI you can look up. It's this thing right here. What an ABI is it's a thing where people get together and they say, all right, look, we've got the operating system, we've got user mode code, we've got multiple compilers, we've got multiple languages. All of this stuff has to call each other. Maybe someone wrote a C library and it's got to call Python. Maybe Python has to call Perl. Maybe Perl has to call into the operating system, and maybe the operating system has to call back to some C code. All of these people need to have an understanding, if they're going to work together, about how functions are called and how return values come back, right? This is just a fundamental aspect of programming, and it needs to be obeyed. Because if it didn't, you couldn't have anyone call anyone else. Any given compiler could call code that it wrote itself, because it knows how it's going to do stuff like where it's going to put parameters and where the return values come back. But remember, that stuff is not specified at the processor level. A processor is just a machine that has registers and memory accesses. It doesn't specify anything about how a function is called, other than perhaps some slight bias towards, for example, the call instruction maybe automatically pushes the location where things were executing previously onto the stack first, so that a ret instruction will automatically pull them off or something like this. And we're going to look at that in a little bit. But that's it. So all the other stuff about, like, oh, where does the first float go that you pass? And where does the first int go? And what if I pass a structure? Where do all the members go? What if I pass a pointer to a structure? What happens, right? All of that stuff is defined in the ABI. So once you understand the ABI, you understand how functions are called. So fortunately for us, we don't really need to understand very much about the ABI unless we're actually producing machine code, which we're not really doing here in most cases. In Handmade Hero, certainly we're not. But when we look at the assembly, it's important to understand that the assembly we're looking at is generated that way because it is complying with the ABI. It is using the stack, it is using the registers, it is using them in a way that complies with someone's specific definition of how code was supposed to call other code on this platform, this operating system, and everyone is supposed to obey it, right? So Linux lays down the law for Linux. It says anybody who's operating in our ecosystem, this is how you're going to call stuff. Just get it straight, right, or something. And again, they have to do it for each processor type they support as well, because the processors differ. So whether you use a register or a stack or memory or whatever, right, that stuff has to be defined per processor because the processors differ. But for all x64 processors, for example, here's the ABI. And everyone has to obey. OK. So we know that the linker is going to obey the ABI. So we know that no matter what we tell it to do in C, it's going to figure out a way to do that properly in machine code. That's great. We don't have to worry much about that. But what we do have to worry about is the compiler itself, when it's actually going to go like process our code. It needs to know what to, basically how to do the code gen to conform to the ABI for whatever function call we're doing, which is why it needs to see a function signature. It needs to see the function signature so it knows how to set up the call stack and the return value information so that it can properly call the function, right? It needs to know that information. So that is where we get to the weird type def part of C, right? So let's say that I do a void star function equals 5. We know this works. We know this takes the address of 5 and puts it into void star function, right? And now I want to call it. Well, I can't, right? And the reason I can't is specifically I get a compile error. The reason I can't is for no other reason than it simply does not understand how to conform to an ABI when it doesn't know a function signature. It doesn't know what it's supposed to return. It doesn't know what arguments it's supposed to pass or what they look like. So there's nothing it can really do. If it just has a void star, it can't call a function because it doesn't know what that function's signature would be, right? So what we need to do is tell it what the parameters are and what the return value is. Because this syntax in C is telling it to treat this as a pointer to a function, and we'll put the arguments in here. This syntax is function call syntax. When it sees something with open close parentheses, that's a function call. It could do this, it could call this location. That part it knows. What it doesn't know is what's coming back. How do I create code that obeys the ABI? Maybe I can infer, because this is closed with nothing in it, that there's no arguments. Okay, but I don't know what it returns. I know you're assigning it to an integer, but maybe it returns a short. And a short to an integer conversion would be okay here. Maybe it returns a whole struct, and this is an error. I don't know. I really don't know what to do. So what we need to do is we need to give it enough information so that it can properly generate the code that conforms to the ABI. And furthermore, again, since we're in C++, some of the information we're giving it isn't strictly for complying with the ABI. It's actually also there to do error checking so that we don't try to call a function in a completely incorrect way, right? OK, so that's where the typedef stuff comes in. The typedef stuff comes in to give us a function signature in a way that we can use so that we can do stuff like calling functions. So if I say int, number function, what I've done here is I've typedef the function signature so that I can now use it to say this is the kind of function that I have, right? This is the kind of function that I'm pointing to. And again, nothing has changed in the code at all at this point on this line. I am still just moving an address into this function pointer. That's all I'm doing. The only difference is I have now given the compiler at compile time the information it needs to know how to generate code conformant to the ABI to generate the preamble to the call instruction that will successfully set up the stack frame and the return stuff processing for this function, right? OK, so now we compile and we get code that actually should work. We can step in here. Again, I'll show you the disasm here just as we've been doing. You can see it exactly as it goes before. We do a call here, and now the only change has been we load in the address first, and then we store that address to a place on the stack, right? And this, again, is just because the code is not optimized. We would probably just call straight out or something similar. Although maybe we wouldn't, because RAX is going to get destroyed by the return, so maybe it wouldn't. Who knows? Point being, what the code does here is it's loading the address of the function to call. It's then storing that to the stack at the location. This is the space on the stack that was created to store our local variable. It's a space that was created to store function, right? So this is function. It's then going to call it. And again, I can continue my trend of putting these as global variables so they become named so you can see that, right? If I compile now, oops. If I compile now and then do this step, you can see exactly what's happening here. I load into RAX the location of the function. I store that location out to my function pointer. I am then going to call through my function pointer, right? Which will call out to here. It will put 5 into EAX. I will then move that EAX into my number, my global variable, and I am done, right? And again, we can look at that happening in the debugger one step at a time, right? Here we go. I'm going to load in that address. I'm going to move that address out to the location on the stack that is corresponding to that global variable function pointer. I'm going to call through that function pointer, and you can see now that I've arrived there, right? And you'll notice this is the function pointer's location. So I'm calling through that pointer. That's what this bracket syntax, this keyword pointer bracket syntax means. It means look up what's the address at this address. Don't branch to this actual address. So it's going to get this that we stored there. It's going to use that and branch through it, right? Intel x64 is crazy sysc instructions. They can do stuff like go fetch a piece of memory and call in one instruction, right? That's just Intel's encoding for you. It's a sysc style encoding. So anyway, we're going to branch up there. You can see we do. We move into EAX exactly as you expect. There's that EAX. We hit the ret. Here we come down here, and we do the mov to put into our global variable the value. And now if we were to look at this value, as we did before, we would see, oops, again, we would see that it was 5 as we expected, right? No big mystery here. All I have done is shown how to call through that function pointer. Again, it's exactly the same as if we had just inserted 5 here, except now instead of calling having that call site be patched during the link phase to actually point to a specific location in the executable. Instead, what it's doing is it's creating code that's taking that same patched address. It is still patching the address. Instead of patching the address at the call site, it's taking that address. The linker is putting that into code that loads it into a global variable, and then it's calling through the global variable. Hopefully you saw that happen. Nothing weird, right? It all makes pretty good sense to you, right? Okay. Again, let me show you yet one more way just how unmysterious this really is. Let's suppose we just want to make our own function. I don't even have this anymore. It's gone. Okay? I want to do that. And if I wanted to do that, I need something here. I don't know. I need some kind of thing for my function, right? So how would I go about doing that? Well, we have the compiled version of this function, right? I mean, we've got it. So let's suppose I step here and I go, well, this is the code for that function, right? I mean, this is the code. It's B8050000C3. That's the code, right? That's it. I mean, I can look at this location in memory in the memory watch window, right? I don't have to believe the disassembler, and here it is. So that's the code for 5. That's just the code, period. There's nothing else to say about it. That's the code. So this is literally, and I'm going to just cut and paste it out here, this function 5 literally compiles to this byte sequence. Okay? This is literally the code for this function. That's the code. That is what exists in memory at the time it's executed. When we call it, that is what the processor literally sees, right? So what that means is once I've got it, what do I need this for? It's not necessary, right? Because I now have the compiled code for 5. I'm not even going to bother passing it to the compiler, right? Screw it. Forget it. So now when I compile, it's like, well, I don't have this function 5. I'm like, I don't care. Just use this. I just want you to branch to that. And it's like, well, I can't branch to that. It's not a function. And I'm like, well, you know what? Pretend it is. Just trust me on this one. Pretend it's going to be. And of course, this doesn't. OK, fine. You know, if you don't want me to do that, let's just say point to the beginning of it, right? So I'm just saying, look. That very first, and in fact, I could probably do this a little bit cleaner if I did a pointer there. But anyway, the pointer to the first byte of this thing, just pretend that's a function pointer, right? That's all I told it to do. I'm just like, trust me, it's a function pointer, right? So then I'm like, OK, let's see what happens. And there might be some caveats here, but we'll kind of get to those later. So let's see what happens. If I look at my disassembly here, you'll be like, you'll kind of take a look at what's going on. Now we're like, hey, you know, this is a little bit weird, right? Because you can see now when we're kind of looking at this, we have code for 5. Code for 5 isn't defined anywhere, though, right? So when I look at this, I'm like, where is the code for 5 code? And the answer is that basically we've only been looking at the code section of an exe. But as you saw before, when I kind of like brushed it aside because I didn't want to talk about it yet, when we had that 2.0 times something, and I was like, oh, it put that float in the data segment. This executable, this object file, in addition to specifying code, which is what it's dumping here in disasm, it also has data. And so there's different sections. Like I said, this conf object format is kind of like a pack file. It puts in, or sorry, I should say the object file format is kind of a pack file. It doesn't have to be conf object file format. Where it can put data in there as well. And of course, you can understand why this might be the case. It's not uncommon for code to have a bunch of tables in it and constant values and string constants and all that stuff. That stuff all has to flow through the whole process because the executable, when it loads, has to have all that data because it's referenced, right? So in addition to having the code segments, which is what we see when we do a disasm, we can also ask it, and again, this is going to tax my memory on how to do this, we can also ask it to see parts of the data that are that are purely data in nature, part of the object file that are purely data oriented in nature. And I don't know how to do that exactly. There's the raw data. I don't know how to tell it to actually print it out, is the problem. Show me how to print it out. Let's see. Directives, dependence. All, well, I don't know. What if I said all? Would all help? Probably not. Oh, hey. Yeah, it did. Yeah, it does. So you can see if I do all now, I'm getting a lot more stuff, right? I'm getting all kinds of things that maybe I wasn't getting for before. And what you can see now is we've got a bunch more information. Here's the symbols. Here's all the symbols we have. Code for 5 is there, right? You can see its relative offsets and all this stuff. Here's a bunch of raw data. And what we can see, this B80500, you know, somewhere in here, that's going to be, right? And I think we probably can find it. Let's see if we can find it somewhere. I should probably just load this in and search. But we should have, again, some information about exactly where it is when we actually look. Let me go ahead and do a less here and see if if I can find it. So let me look for B8. No, we didn't get it. So I don't know. Maybe all still doesn't actually tell me all of the data, because you can see like it's got this here, and I don't know where it's actually put it. I'm not sure I want to spend the time trying to tell dump bin how to do it, but just trust me, it's all going to be in this object file. You can presumably coerce dump bin to show it to you. At the very least, if I wanted to, right, I could also just ask. Do I have list on here? Yeah. I could presumably also ask to just show me the OBJ file, and in a hex editor, we could just come in here and actually find it, right? Because somewhere in here is going to be code for 5, and we can find out where that actually is, and I can search for it, right? So if I want to, I can look for that B8, and here it is, right? So there's that code, the B805 code, right? It's the B8050000C3, which is this code right here. So there it is in the executable, right? It got stuck, and somehow we could, if we had more time to play with dump in, we could probably find a way to more cleanly do it. And of course, it says here what the offsets are, so we could have known presumably as well where in main.obj it was, right? But anyway, point being, now I produced an executable, which is going to call that specifically. And so if I look at the dump bin here for my main, there it is. What you can see is now we're loading the code for 5 address, right? We're loading that in, which is just our array of data that we put in there. We're, for whatever reason, doing this array indexing. And so, you know, I think this is just because we haven't specified that the compiler should do any optimizations. It's actually doing this 0 part here. So you can see what it's doing is it's saying, like, OK, let's go 0 far into here, right? Let's go 0 far into this array. It's like, all right, I'll go 0 far into the array, which is still exact same place. And then it's actually loading that into the function pointer, and then it's calling that function pointer. But fundamentally, all it's doing is calling code for 5, right? That's all it's doing. And presumably, I don't know if I can make that less obtuse. I don't think I can make an initializer list in any other way. I want to do it. I would like to do it so that it wouldn't do that. But you can see how it wants to. It really wants to make me convince it that it's a pointer, because it's thinking of this as an array, right? And you know, I mean, we could sort of fake it out by having it do something like this. Actually, maybe I'll do it the other way around. You know what? I'm not going to do that. It's too much. You'll just have to bear with me or believe me when I say that's what that code does. Because again, let's go ahead and there we go. Because this is still going to be the simplest way, I think. is just to show it, right? So you can see here it's loading in the address. It's not, when it does this advance by 0, that's not going to do anything, right? It's pretty much entirely, sorry, allergy season. It's pretty much just going to load that in. It's going to advance it by 0, and then it's going to load that in and call through it, right? That's all it's doing. So it's not particularly interesting. It's really just calling directly into that address. So let's take a look at what actually happens when we do that, right? When we actually do that, we come through here, right? We end up with that function pointer, and we're going to make a call into this here. And lo and behold, when we make a call and we're here in our data segment, what do we find? The exact code that we expected happening, right? Here is the code that moves 5 into EAX, right? And of course, this is the caveat that I said I was going to have to deal with. And then we're going to return, right? That's exactly what we want to do. Now, what you'll notice is even though this is totally valid code, I get an exception here, right? Access violation executing location. Why are we getting that, right? Why are we getting that? Well, the reason that we're getting that is because we're technically not allowed to execute data that we haven't pre-told the operating system is executable, okay? Why is this? Well, it's the same as the address space layout randomization problem. The problem is that security people get kind of overzealous, or maybe you would say just zealous, because they're not necessarily overzealous. They are trying to prevent real hacking problems. One of the things that CPUs added recently was the concept that in addition to memory pages being marked readable or writable, they could also be marked executable. And if a page was not considered executable, stuff in it couldn't be executed. Now, why would you ever need this? Because you never do. Well, the answer is because hacking, right? No reasonable programmer ever really needs this, because if you wanted the thing to start executing somewhere, you wanted it to start executing somewhere. But to prevent against hacks, it's obviously interesting and useful to be able to say only things that the operating system has previously said can be executed should be executed. So if somebody manages to slip some kind of a hack in that tries to call into a data segment somehow, that will be prevented, right? And it prevents like stack hacking, because stack is data, right? And so if you can get some code on the stack and then try to branch to it, the operating system will immediately fault you because that page was not marked as executable. It's stack, it's memory, right? And so that's what's going on here. So how do we prevent the operating system from doing this and get our code actually marked as executable? That unfortunately is a little bit harder, certainly, but we can certainly try, right? And this is where things become a little harder to read, but we'll do our best. So what happens here is basically we need to sort of let the compiler know that this data that we've got here needs to be executable. And the way that you do that in Windows is via the virtual protect call. You can see here the list of memory protection constants that Windows accepts. Page execute is the one we need. So what we really want is sort of to tell Windows, hey, I need you to allow me to execute some memory that I'm going to specify, right? So let's just do it. Let's just do it and take it all the way. So here's a virtual alloc and a virtual protect. I'm going to call both of them, right? And this will actually set us up for the final thing I want to talk about anyway, which is how the operating system and you agree on locations of things, right? And first I'm going to blow my nose again because allergies are awesome. All right. So first we need to get some memory, and then we need to virtual protect it. Although actually I suppose I could probably try to just virtual protect the page. I don't necessarily need to allocate it. I could just say, let's virtual protect the code for 5 page. I just don't know if it's smart enough to take the base of that address. Describes a starting page of the region whose access protection has been changed. All pages in the specified region must be within the same reserve region allocated. Reserve. They can't span adjacent reserve regions. So the problem here, the reason I can't really use virtual protect is because I don't know where the base of the allocated range is. So I'm basically going to have to do something like this. I'm going to have to call the operating system and get a page of memory. I'm then going to have to protect that memory as being legal to execute. I'm going to have to copy the code for 5 code into there, right? And then I can jump to it. So let's do that. Here's my char unsigned code for 5. I'm going to get it from virtual alloc, right? That's not the way this actually works, but that's basically what we're going to do, right? Then what I'm going to do is I'm going to virtual protect that page. And then what I'm going to do is I'm going to copy the bytes that I actually need in there, okay? So I'm going to do this. Okay? So let's look up the function calls that I need. So here's virtual alloc. And here's the prototype for that. I'm going to cut and paste that in here. Just so we can see it. So we have a void virtual alloc. We have a void star LP address. I'm just translating for lack of, I don't know the correct term. I'm translating the Hungarian notation, if you will, into sane types temporarily. Here's the virtual alloc call, right, that we actually need. There we go. And then we also need that virtual protect call. Oh, wait, no, we don't. You know why? Because we can actually pass the protection to it directly. So we only need virtual alloc. That's all we would need. And then we should be good to go. So size t in this case, we need the definition of. So what I'm going to do is I'm going to cheat again and use the previous Win project here. Sure, we'll save that. Go ahead. Let's go ahead and look that up. Win through project. So we need to know what is size t. Go to definition. And so there it is. So it's really just one of these underscore underscore int64s that's unsigned. So let's go ahead and put that in there. There we go. And so now we have the function prototype for virtual alloc. I'm going to call it. I don't need a base address. The size can just be one page, let's say. In fact, we really only need 64 bytes, but it'll round it up. So, I don't know. It's really going to allocate a page anyway. I might as well put one in there. The allocation type in this case, we're going to need type memory allocation. Allocate pages, and we want it to actually commit. So we want these pages to actually be used for us. So we need this constant, right? So there it is. And then finally, we want the correct memory protection. We don't need any of that stuff. So we just need the memory protection constants here. Page, we just want everything, right? We want to be able to read, write, and execute. So we want everything. I don't know if that's if they have a convenient one of those. Let's see. Read, write, read only, no access, execute, write, copy, execute, read, write, execute, read only, or read, write access to the committed region. So this is the one that we want, I believe. Let's go ahead and paste that in there. All right. So now I'm going to compile. We don't need this anymore. It's gone. And what you can see here is we pretty much are good to go in every respect except for one slight problem, and that is that we don't currently have the way to link with the virtual alloc call, right? So that's what we now have to figure out. Oh, well, I guess you know what? We probably even do. Let me just see if we do. We should actually. Yeah, I think we actually can. I take it all back. So in theory, we probably can, and I'll explain this in 1 second. I apologize for. This is the stuff I want to get into, but I don't. Oops. Let's see. Referenced in functions, main CRT startup, unresolved external. So it does actually need me to specify kernel 32. So I will. And so let me just, and again, I apologize for getting a little bit ahead, but I want to finish talking about the execution part, and then we'll move on to all the stuff that I just did in a second. So let's go ahead and get ourselves the one other thing we need. And I'm going to, again, keep us to only stuff that's actually in our directory so that we're never going outside of it, so we can look at literally everything that there is. So let's go ahead and grab that out of here. Let me see if I can find in here. I don't know that it's in here. I want the platform SDK. Let's see. Is it in here? All right. I think that's sufficient for our purposes. Let's copy this fellow out and into all right. OK. So again, you'll have to bear with me for 1 second because I want to tackle this part separately. So we're going to have to talk about libs and so on. All right. So now, in theory, if I jump back here, and again, like I said, I'll explain all of that. I just don't want, I want to show you the executed code first part to finish off that last part we were doing. Let's go ahead and take a look at what this code does now. And unfortunately, it gets a lot more complicated, like I said, but we have no choice because I don't really know if there's any way to specify maybe there is a way to specify to the loader that you want execution protection turned off. There probably is somewhere, but this is the fastest way I could think of on stream to do it. So we can see down here where we actually do our function call, all of this right here is the code, again, unoptimized code, but code nonetheless, to just move, to do the construction of the code in memory. So let's watch it happen, right? Right here is our call to virtual alloc. And that call is going to return in RAX the pointer that we got. So here is, in theory, that pointer, right? And now we're going to actually start moving stuff in there. And we should be able to actually look at it, right? If I was smart, I would have saved that. But we know it's RSP plus OX20, right, according to this. So it should be, or at least it should be in there, right? Let me actually, let me get that out in a little bit more sane fashion. All right. So let's try that one more time so I can make it easier on myself. So here's our call. Again, should be our call, our first call out to virtual alloc, right? So in here, where we are on the stack right now, if we look, we're in kernel 32 inside virtual alloc, right? So I'm going to jump out of that. That's after the virtual alloc has completed. RAX, now the register itself, has, in theory, anyway, the pointer to the page that got allocated. So now if I take a look and I do a char unsigned and I look at that location, right? So there's looking at this location. And I look at, say the first 16 bytes of it, that's the page that Windows allocated for us. Now what I'm going to do is step through the code that literally all it's doing is filling this out with the code. So you can see it doing that. Here's our B805C3, right? And that's the end of it. So it stops there. This is just untouched, right? Now we're going to call into that memory. And this time, when we get there, again, it will look exactly the same as it does before. But now, note some things. First of all, you can see that this time when we step, it works, right? We've done nothing differently now. The only thing is, instead of it being in memory that was supposed to be part of our data segment, which Windows does not set the execution bit on when it loads it into memory as part of our executable, this time we did it in memory that we allocated. And when we allocated it, we told Windows specifically, hey, this is going to be executed. So allow that. Set the memory protection on this page so that you will allow that. The processor will not throw an exception when that happens, right? We executed it. It did exactly what we wanted to do, right? And now we're doing a return call. We get back here. We finally complete the thing that we wanted to do, which was actually setting our global variable equal to 5. And remember, we can actually now look and verify that that is the case. And lo and behold, there is our 5. So what we have done now, literally, is we actually made essentially our own compiler, right? We made something that can do exactly one thing, which is create a function that can return 5. So it's not a very good compiler. It's not really a compiler, I suppose. It's a code generator, let's say. It can generate exactly one piece of code, and that piece of code is something that returns 5. But wait, there's more. Is it really something that can only return 5? Well, not really, right? Because we kind of know that this 05 right here is the constant that's getting returned. The Intel encoding happens to encode that return as an immediate, which means that the instruction itself encodes the value that will be moved to the register. So really what we've done is a compiler that can generate a return of any byte that you want, right? And furthermore, it's really more than a byte, because this 1234 here is really 500. This is the 32-bit value encoded as an immediate into the instruction that is getting returned. So if we wanted to, we could produce a piece of code that returns any value by patching that location equal to the thing we wanted to return. Let's prove it, right? Here's an int star. I'm going to say that this location here, this code for 5.1, I want to treat it as an int star, and I'm going to put the 5 in there. OK? So now let's step in and see what happens to that particular piece of code, right? Here we come down, and let's take a look at what we get. You can see in our hexadecimal display here, B85C3, right? So that's the old style. Let's go ahead and change that now to some other variable. Let's say 15, and let's do the same thing. We come through here. We take a look at what we get. Oh, you know what? I got to remember, since address-based layout randomization, every time I call this, every time I call virtual alloc, it could give me back something different. There it gave me back that address, for example, instead of, so I got to look at the right address every time, right? So here we go, and we fill it out, B8. And now you can see we put 15 in here, right, instead. There's the 15. And now what we're going to do when we call into our function, you can see, hey, look, it's no longer a move 5, it's a move 15. So when it returns, it's going to return 15 instead of 5. And when it moves out into our global variable now, the result of our code is going to be something different entirely, right? So here we go, looking at that code. There's our 15. So now we really do have a real code generator in a sense. We can generate something that returns any 32-bit value, right? So as long as you wanted to implement a language that's only feature that it could do is return a value, and that value has to be a 32-bit number, you've written the compiler for it essentially already, right? That's what we've got. Okay? It's pretty cool when you think about it, because it's really no more complicated than that to do on-the-fly code generation. This is an on-the-fly code generator. It, in fact, can generate any code that you want. If you started giving it some ability to output more than just this simple set of instructions, you can now build any x64 code you want. There's nothing you can't do. Anything you want to do in here, you could do, right? Now, I don't know if I've lost everyone at this point or if everyone is still on board. I'm hoping that everyone's still on board. Let's go ahead and push it a little bit further and just sort of take it to its logical conclusions before talking about the virtual alloc part of this and how the operating system and DLLs and that sort of stuff get bound together, right? So in here, I have my code for 5, right? One of the things that's interesting about this code for 5 is I'm generating some code in here. Could that code call my code, right? What if I needed that code to call something itself? You know what I'm saying? How would that work, right? So let's go ahead and get our 5 back in here, okay? And let's go ahead and take a look right here at what happens if we want to call 5 at, say, this point in our program, right? So right here, we want to call 5. We want to get the result of 5. Back or whatever. Actually, let's see. How would we want to do this? So I want to Oh, and you know what? This doesn't have to happen this way anymore, does it? Yeah. So I'm just trying to think of how I want to do this. So let's say what we wanted to do. Oh, you know what? I just realized. This is what we'll do. This is totally what we'll do. So let's say that I wanted to return whatever I get back from 5. OK. So there we go. Right? So let's take a look at what actually happens in that code right there. OK. So now I'm going to step into this code. I'm going to come down here. You can see when I'm doing this sort of operation stuff here, you can see the move RAX. You can see the move. This is the call to the function 5, right? Here is the call to that function, right? And it's a little bit complicated if you take a look at it, right? Because what's happening here is really kind of confusing, right? And let's try to break down why it's confusing. What's happening here is we're calling essentially relative. How do I know that we're calling essentially relative? Well, if you take a look at what's happening here, the bytes for this call in no way encode this address, right? So here's the address that we're calling, and here's the code bytes for the instruction. Well, I would expect to see this in there, and it ain't in there. Now, what I do see instead is an FFFFFF78. That looks suspiciously like a negative number in 2's complement, right? It sure does to me anyway. And furthermore, since this is little endian, it's really going to look like this, right? Because the smallest byte comes first, which is the 78, then the FF, then the FF, then the FF. So it's really this value, right? And it's that value, I suspect, as an integer, which is a negative 136. Now, if we look at where we're at, 13F591OB3, right? If I look at that hexadecimal value, here it is, right? If I look at that hexadecimal value and I want to subtract 136 from it, right? I would get a different hexadecimal value. What hexadecimal value do I get? I get 13F59102B, right? Something like this, I think, right? Is that what I get? I don't know. Did I type that incorrectly? 13F5910B3, right? OK, yeah. So I know that I'm calling this address, right? And so if I look at it here, oops, and I look at the location, and I subtract the two of these, there we go, you can kind of see that it's almost what I would expect, right? It's like, OK, so I have a negative 136, and the difference between the thing that this is saying I'm jumping to and the instruction that I'm currently on is negative 131. So it's almost right, but not quite. But so I can sort of see how it's doing this encoding, I guess, right? But not quite. So just from looking at it, it's a little bit hard to reverse engineer, but it's pretty clear that it's some kind of a relative jump, right? It's like, hey, I know that I'm jumping to here. This is where the instruction is. It really looks pretty darn close, so why is it wrong? And the answer is like, well, the difference between these 136, 131, oh, hey, look, it happens to be 5 bytes, right? So it just so happens that the instruction is encoded based on after the 5 bytes hits, right? After I suck up those 5 bytes, then I get that encoding, right? Then I get the value. So this is a relative call that calls relative to the instruction pointer, right? So if we wanted to generate code ourselves, and we know that we have to write that code into a memory page somewhere, obviously we can't use this call instruction, because this call instruction is going to have to embed a relative call in it, and we don't know where our virtual page will be relative to this page, so we can't very well do anything about it. Now, we could hope that when we allocate the virtual page, we will end up being able to put them, you know, close enough together or something like this that we could still use a relative call, but obviously it's a little dicey, right? So what we'd much rather do is we'd probably rather have something that can call sort of more absolutely, but unfortunately it's pretty hard to get something like that to work. Get the compiler to output something like that so that we can look at it. Because in all these cases, it's going to be calling something that's going to be pretty local in this case. However, we do have some guidance. I suppose I can't set a breakpoint there. OK, there we go. We know that this is going to call virtual alloc, right? So here's a jump into the virtual alloc call. And what you can see is really this is just a secondary jump, which comes out here. And then we get another jump, which is going to be to an address, which is encoded sort of more directly in here, I suspect. Although still, I don't know, this may still be a relative jump 7795D328H, which is not the same here, right? So here we go into another one. Are we actually now we're actually in kernel base. So this is the code we actually wanted to call to here, which is 7FEF, like blah, 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 right? That's the actual address that we were trying to call there, that one. Let me go ahead and switch that to hexadecimal view. And if I step back out here and I look at how that call was structured, well, unfortunately, that stepped out twice. I guess I shouldn't have done it that way. Let me step in one more time. There we go. So there's the jump, again, the initial jump in the table. And again, we're going to talk about a little bit this a little bit more. Here's the secondary jump. Here is the actual code that's going to be doing the virtual alloc stuff, and it does a secondary call in here. But it comes down to this ret. It's at the same location in both cases, 7FEFDA4190. So we know that that's the correct address still. And so if we take a look at where that call is happening, I guess I see what happened. It returned there because those other things were jumps, not calls. So they didn't modify the return address. But I found the piece of information I needed, which is that particular location doesn't get modified. It doesn't get moved around. So if we take a look at what's happening here, we're doing a jump to this location, which again is not this. Then we're doing a jump to this location that's basically reading out of this pointer that's here, and that pointer has the location of virtual alloc, right? The reason for the double indirection has to do with how DLLs are linked, and we can talk about that again a little bit later. So if I take a look at this, what's at this location, what I should see, again, is a pointer to that virtual alloc function. So if I take a look in here, let's see if I don't actually want that to be a void star. To be a void star star. There we go. So if I look at that void star star, I'm saying what's at this location, and the answer is what's at this location is this pointer to this function, which is where I'm actually going to branch to, right? So what it's doing here, at the moment, I guess this table we're in is in the address space for kernel32.dll, which is what we're jumping into. And again, it's sort of a redirection table that's going to move us out to the actual virtual alloc call. So the question is still, none of these have really given us what we would need, which is something that allows us to more easily crib off the compiler something that we could call so that we can call like a location more freely. Maybe, yeah, nothing, I don't know. I can't really think of anything that would allow us to do that. So I guess what I would say here is, given that the only thing that we're going to be able to do is do a relative function call in this case, I feel like what we need to do is just embrace that and go, all right, let's figure out how to call some of our code directly by using that same indirection style, right? So what are we going to need? Well, we're going to need that sequence that uses a relative call, right? So for example, this thing right here, this call keyword pointer, here is an address, and that address is saying, go there, read 64 bytes, and branch to that, right? So this is the sequence for doing that call. This is the sequence that does that. So let's grab those bytes, right? Let's just grab those out and look at how they correspond, okay? So in this case, we've got, again, that jump. In fact, maybe let's use one that's a little bit, do we have one that's not going to be so onerous? Maybe a call that's a little bit. So here's a call that's going to be a little bit less finicky, perhaps. So right here. So this is the call that goes to our actual data, right? And so let's take a look at how that's encoded. So again, here are our bytes, right? This is the location of the code. This is the pointer to the code. This is the location that we are loading from, that we would like to load from. So this is the point. This is where the data actually is, where that pointer is. We know there are 1, 2, 3, 4, 5, 6 bytes in the call, right? So technically, we want to add 6 to this value, which is the one that we'd be starting with, right? And so then let's take a look at if we subtract that away. So if we say, where would we have to go to get there? Let me take a look here, right? And then let's see what we're actually passing in here as the actual values. Again, I'm not sure I quite did that correctly in the reverse engineering there. So I'm going to have to be a little bit more careful here when I'm looking at it. Yeah, because just looking at it, maybe it's going forward. I don't know exactly where it's trying to get that dword pointer. So 308, so it's going forward, right? So that's why this number isn't negative, right? So we're expecting to see this to be a positive number. It is. We look at the hexadecimal, it's 1F5B is the actual value. There is the 1F5B. So that's the 32-bit offset, I believe, that we are interested in. So what this gives us right here is a sequence that would call with a 32-bit offset something relative to our current location, right? OK, so let's go ahead and put that in there. So instead, what we want our function to do is rather than include the code for 5 that we're actually putting here, we want to actually put the call to code for 5 in the generated code. Then we'll just return. We know that C3 does the return, so we'll just do that, right? So we'll call, and then we'll return. Not particularly good code we're generating here, but that's what we're going to do. And like I said, it's the 5B1F part. That's the actual offset. So off we go. All right. So how will we do this? Well, the way we'll do this is first by saying, all right, the code for 5 needs the preamble. For the call, that's the FF and the 15, right? We then know that the 5B1F part, right here, 5B1F, right? And you can see that's 5B1F. The 5B comes first, because it's little endian. 5B1F0000, that's the part that's an int star. So this time we're looking at here, and we're looking at that integer. This is our offset. We don't know what that offset is yet. That's going to be 2, 3, 4, and 5. Then we get to 6, and that's our ret, right? So now what we need to do is we need to have some location somewhere that's going to store the jump location, right? And again, this jump location can now be absolute because the relative encoding is in the instruction that says go look at this location, pull out the pointer, and jump there, right? So let's go ahead and do that. What we need to do is now store in code for 5 somewhere else. Let's say up after our return instruction. We're just going to put in here the actual int64 address that we need, which in this case would just be a void star, right? We need to treat this address as if it's going to be a pointer to something, and we're going to put into it the function 5. Okay? So let's go ahead and compile that. Everything works except for the fact that we need this location. We now know what this location is. We just need to know the offset from where we are that code for 5.7 is. Well, we know we're going to end this instruction at code for 5.5, right? Or I should say at code for 5.6. That's where it's going to end after when it's executing. So all we need to know is where code for 5.7 is relative for code to code for 5.6, because the CPU will have consumed up to code for 5, code for 5.6. Code for 5 is a bad name. Let me just call this code. Or maybe just code. Let's just call it code. just to get me out of that. That was just hard to say. Okay. So what we need to tell it is what's the difference, right, between the address of where we're going to end when we're executing the instruction and where I need you to read the pointer from, which is right here, right? And let's go ahead and compile that. All right. So now let's look at what we've done. Let's go in here and take a look at this monstrosity that we have created. So we're going to come through here. Again, this is our call to virtual alloc. Virtual alloc will return into RAX the pointer that we now have allocated for our code generation. I am going to go ahead and look at it as a car unsigned, and we'll just look at the bytes. Here are the bytes. Now we're going to go ahead and quote unquote generate our code, which just involves us stuffing the bytes in. So you can see us stuffing the bytes in here. There's the FF and the 15. And remember that FF and the 15 are just being hard set. Now what we're doing is going to insert the offset necessary to call, to get to this part of the code, right, to this part, and it's just a piece of data we're sticking in there, but it's just that part of the allocated memory, right? So what we need to do is fill that out. And that should happen right here, or somewhere soon. There it is. OK. And that's correct, actually. It's only 1 byte. Now that I think about it, that's what it should be. It's only 1 array. Then we're going to stuff in the return part, right? And now at the end of the code, so this is all of our code. This is the call instruction plus the offset, which is 1 byte. The offset to look at the, so it knows where to load the pointer, right? Then the return instruction. And now right here, which is where we've told it to look, we need, right here where we've told it to look, we need to put the 8-byte address of the function. And that's what this code is going to do right here, right? And there it is. So that's the actual address of the function. Let's see if it actually did that correctly, because we should actually be able to find 5. It should be right here. So what we should be seeing is 310-8C F813, right? 310-8C F8, oh, oops. 310, sorry, C8, or 8C, yes, F8. F8, I'm just reading that wrong, but yes, that's exactly right. But my reading comprehension skills are not great. So we've loaded the location of this function, 5, that the compiler generated. We loaded it into our code page, right, that we created. And that's where relative addressing, we told it to go get the result when it does the call, right? So now here comes the moment of truth. Did we do it right? I don't know, right? That was pretty fast and loose that I was playing there, certainly. So we're going to have a load here of RAX into this thing. So that's this right here where we're loading in the function. And then we're going to call through there. OK, so this is the moment of truth. This is the call. We're calling through it. Here's our generated code. It's beautiful, isn't it? Look at the code we generated. Aren't you proud of yourself? You should be, if you've made it this far. Here we are doing our load. I'm sorry, doing our call that loads the address to jump to out of this location. This location was encoded relatively right here by saying 1 byte after the end of this instruction. That is where we're going to go, OK? That's exactly where we put it. We put it right here, so we're hoping it loads properly. What you'll notice is the disassembler doesn't know that's what we made. It still thinks it's code after the ret. We stuffed data in there. We didn't tell it, right? So it's going to go ahead and disassemble that. So it thinks we stuck in an XOR mov add, right? That's not what we did. But it doesn't know. The disassembler just disassembles what's in memory, assuming that it's code, right? But instead what we're going to do is we're going to branch to the location found at this place. Let's see whether that actually is, if we actually encoded that properly. So let's say that's a pointer to a void. Here it is. And hey, look, it's got the 13F8C1030 in there. Hopefully, I think that was the right address, right? So we're loading the address. We're going to branch. Boom. There we are back at 5, right? It's a great day to be alive for programming. Everything worked just great. Here we are at the actual call site of 5. This is where we would have, not the call site of 5, but the place you go to when you call 5, just as if the compiler called it, but we called it. We generated the code to call it, right? Here we are. It's going to return, and it's going to have placed in EAX the value of 5, so that's there, right? When we ret back out, we come to our ret. We're not going to touch that, so that's fine. It's going to leave that return value in there. And lo and behold, through our own code that jumped into the code the compiler generated, we got that value 5 out. And here it is, ladies and gentlemen. It has been written out to our global variable just as we would have wanted. And if we look at that global variable and see what it contains, like so, oops, that is if I can type, there's the 5, right? So hopefully that demystifies some of that stuff. The code that the compiler generates is just bytes. Those bytes, when they are initially compiled, may have empty spaces in them that are just mentioned as a symbol is going to go here when you link. The linker fills in all of those symbols that are known at link time, although there may be some that the operating system has to deal with, and that's the part we're going to get into now. But mostly that's what happens. All of that code bytes that were generated, they get loaded into memory when the operating system executes your program. And you can look at them. A function pointer just points into those bytes. That's all it does. And you can do anything you want with function pointers. All the way down to what I just showed you, where you can just make up the code yourself, tell C what kind of code you made, and it will dispatch to your code just like it would dispatch to its code. No difference. Furthermore, you can actually snap a pointer to code the compiler made, feed it into code that you make, and actually call that. So you can call into your code and then call back out again. None of it's a mystery. It's just bytes in memory, and function pointers are just those pointers. And all that any of this other stuff does is it just informs the compiler at the call site, what does it have to do to dispatch to that address? That's all the function signature really tells it, right? OK. Time to finish up the understanding of what's going on with these function pointers now to answer the last part of the question that was posed by the email that I received. How do things work if you have two separate actual executable pieces that are produced at the end? Because hopefully now you've seen there should be no questions in your mind about how an individual program works in terms of function pointers, right? You can see that the code that's generated is just call instructions. It's just going to get the pointers from wherever it needed to in terms of like either those symbols were specified by the compiler initially when it generated a piece of code, or that can be made by us where we allocate memory and tell it to call it. So it's just getting a pointer from somewhere reasonable, and off you go. It's all under your control, and you have the ability to specify how it's going to happen. And the linker follows very specific rules that we have now investigated, and so you should have no trouble understanding how that's working. You can even use tools like dumpbin to inform you if you are confused about what the linker is doing. OK, so now the question becomes, what happens with stuff like this call? This virtual alloc call, we never defined that, right? And you saw me have to do a bunch of mumbo jumbo here. I had to insert kernel32.lib onto the end of our link line in order to be able to call virtual alloc, OK? And the question is, how does that work? Because virtual alloc is defined nowhere in any translation unit that we have. And in order to get access to it, I had to do a kernel32.lib. Does the code live in there? And if the code does live in there, well, the allocation is something that the operating system has to do, right? So how does it tell the operating system that it needs to do an alloc? What's happening? How does any of this stuff work, right? OK. Well, so let's start at the very, very beginning. Initially, there was no such thing as the stuff that I'm about to tell you. Earlier computer programming, like under MS-DOS and stuff like this, or going further back, let's say in the Amiga days might be a good example. When you wrote a program, you had the option of writing a program that would be the only program that was running on the system. So there wasn't really an operating system per se in a lot of cases. there was your code. And whenever your code needed something to happen that related to the actual hardware, what you did was invoke an actual BIOS interrupt. Now, what this means is you were actually telling the processor, I need you to jump into code that's actually stored in ROM, in the computer, hard-coded into the hardware. And that is the place where anything that I didn't write occurs. So you're literally talking about like the firmware that's in the ROM that's mapped somehow in memory. Who knows what's going on depending on the system architecture, blah, blah, blah. The only things that you would be calling, quote unquote, that weren't your code were hardware operations. Okay? But as the understanding of operating system ecosystem sort of matures over time, and this is not like contemporaneous with Amiga and MS-DOS were also systems like VAX and so on, where this had already occurred. So it's you know, it wasn't like it happened only as Windows NT happened or something. But anyway, as operating systems mature, they tend to end up at a point where now everything that your code does, if it's a user kind of program, so not the operating system, but user mode code, it no longer directly interfaces with the hardware. The reason for that is because the operating system is required to mitigate concerns that happen between programs. What do I mean by this? Well, if I am trying to allocate memory in a program I wrote, but it's a multitasking operating system, so somebody else's program is also trying to allocate memory. Well, if we both talk directly to the hardware and said, here's the memory I want to use, right? We might pick the same mapping in memory and overwrite each other's changes, or who knows what, or one of us would update the memory mapping on the CPU without being aware that the other person updated it and clobber their change. Who knows what happens, right? So the operating system has to step in here and provide a set of API calls which will mitigate this sort of like, it will sort of solve the collective action problem. It's sort of acting like the government does, where you've got private citizens who want to do various things, and the government has to say, okay, let's arbitrate who's going to do what when, and who owns what property, and so on, right? It's doing that same thing nowadays, the operating system is. Okay. So in this case, what we have is a modern-day operating system provides usually a very large surface of API functions. And the way that this works is that when your code is initially starting, when your executable is loaded, there is a secondary link phase. So very much like the OBJ files that we had, where we had the compiler produce OBJs, which had symbols in them that were kind of missing, right? They were sort of saying, well, I know I need to call bar here, but I don't really know where that's going to be. So just when you find out when it's going to be later on down the pipe, put in the address here so that this code will work, right? So what the operating system does is it basically does that same thing to your code in another link step that only happens when the executable is actually loaded. That's what's actually going on, right? And so if we take a look at what's happening, we can now start to inspect that process. Let's take a look at this virtual alloc call, for example. I can go ahead and do a dump bin like we were doing before on our code in main.obj. And what I can see up with the virtual alloc call, you can see right here that the same sort of thing happened that was happening to our stuff before. Do you see that imp virtual alloc there? Now, imp virtual alloc is nowhere to be found, right? Our code simply does not have an imp virtual alloc. So the question becomes, where is imp virtual alloc? What is imp virtual alloc? It's a symbol that's getting inserted into our code that no one has defined. And that is how we get to what that lib was that I placed on the link line, and that starts to inform how the dynamic linking process on Windows actually works and how things are connected up to each other, right? So if we go and look at how this works, that link line, you can see that I had to put kernel32.lib on there. Well, what is kernel32.lib? Kernel32.lib is this file that I copied in because, like I said, I wanted everything to be in here. Oops, I wanted it to be lowercase as well because I like things to look lowercase. There we go. Let's pretend that I had done that originally, and let's do another directory. There you go. So looking at this here, kernel32.lib, What is that file? Well, a .lib file is really nothing mysterious. A .lib file is really basically the same thing as an OBJ file for all intents and purposes. It's a pre-bundled set of OBJs, basically, that you can link to so that you don't have to have all the OBJs that actually created it lying around. So it's sort of like, instead of producing an actual executable that you're going to ship to somebody and say, here, run this code, if a developer wants to ship something to another developer and say, hey, here's a bunch of code that I pre-packaged together, you can call it and link it into your executable on your link line. A lib is just a way of bundling a bunch of OBJs together and providing them to you to call. So that's exactly what this is, and what that means is we can look at it with dump bin just like we would look at an OBJ file, actually. So if I want to take a disassemble of kernel32.lib, I can, right? Now, unfortunately, what you can see here is, since this is an import library, we don't get very much information out of it, right? It's not willing to give us a disassembly of this because it's in a specific format. Let me see if I can do this with a /all. It's in a specific format that's really only job is to provide a dispatch table for a DLL. And so I'll kind of get into what that means, but you can see it all is kind of scrolling by here. Probably not super necessary. Here you can see, yeah. Let me get this into something I can actually. There we go. All right. So here is kernel32.txt, which is the dump bin of kernel32. And what you can see here is what we have in this library. And it was my bad for trying to disassemble it. You can't disassemble an import library. An import library is slightly different from a regular library, again, just because it's made to specifically instruct how a Windows the linker how to create a program that's going to bind to Windows. But it's still basically the exact same thing. It's just a series of named symbols, and those symbols are there to tell the linker how to patch up information. And what you can see about this library is that this library, all it has in it is a bunch of basically names, which are imp and then the function, and it also has that function. And all of these functions are all the functions that exist in Windows's kernel services, right? Now, I don't know if I installed depends on this machine. I hope that I did. I'm not sure how to find out if I did. Do I have it? I hope that I do. Depends. Anyone? Here it is, yes. Depends is a program that we can use to inspect DLLs. And basically what it is it's something that takes the DLL and shows us what's contained in there, right? And so let's talk a little bit about what a DLL is to begin with, and how it relates to the import library. So what I'm going to do is I'm going to go into the Windows System32 directory, a hilarious name considering the fact that it's actually 64-bit now, but hey, legacy. And this is the actual, even though it's called kernel32 and it's in the System32 directory, it's actually a 64-bit DLL. For backwards compatibility reasons, they kept the names the same instead of calling it kernel64. Yeah. Anyway, I'm going to open up kernel32.dll, and what you can see in kernel32.dll in this program depends. You can see here all of the functions that kernel32 actually exports. And so what is a DLL, and why do we care, and what is this actually giving us that anyone needs to actually know? Well, all right. So what you can see, first of all, is, like, for example, let's take virtual alloc, because that's the call we actually needed. That was the only call that we're actually using in our code, right? Here's virtual alloc. You can see right here, it says where virtual alloc is in the DLL. It has some other information here, like ordinal, which is a way to bind things by number instead of names. Not really important to us now. But there's that virtual alloc call. And the other thing that we can see is if we look inside the lib, you can see that we've got those same exact things. You can see, like I said, these correspond exactly. You can see them here, virtual alloc for ex, free, right? This import library that we dumped has the exact same structure as the DLL in terms of what's in it, right? They're not the same, but they correspond quite directly, right? So what this is actually a way of describing code. A DLL is a way of sort of bundling up a bunch of code. So a DLL and an executable are almost exactly the same. They contain almost exactly the same stuff. The only difference is the DLL is basically not standalone. It's designed to be code that people call into rather than executable, which kind of launches and does its own thing, right? And so a DLL, which stands for, of course, Dynamic Link Library, is a library that's of code that's been precompiled that you can just run. It's not a lib. It's not a library like in the linking sense of the word, like we were just talking about. It's actual code, completed code, with all the symbols resolved. And it just has a bunch of entry points in it that you can call into that do something specific. So in our case, kernel32.dll has the code for virtual alloc in it. That's what it has. What Windows will do when it loads your executable is it will map into your process's memory space these DLL code. So when our program is loaded, it knows that it needs to map kernel32.dll in, and it knows that we need the code from kernel32.dll to complete our execution. Specifically, we need virtual alloc, right? Now, how does it know that? That's where the import library comes from. An import library is specifically what you pass on the command line to the linker that says, here is a DLL, right? Inside kernel32.lib, it basically says, there is a DLL called kernel32.dll. Here are all the entry points that that DLL has. And so if someone wants a symbol like virtual alloc, I've got it. Here's where it, and the way that you're going to resolve that symbol is in the executable. When you output it, you're going to put in a line that says, I need kernel32.dll, and I need virtual alloc from it. I need you to patch that value in right here. OK? So let's take that a little bit further. Here's my depends. Like I was saying, I'm going to load. Depends allows me to look at basically what's in, I've been saying all this time, it puts this thing in the executable that you can load. Depends is basically something which takes an executable file, either a DLL or an exe, because like I said, they're basically the same. It takes one of those and it goes, what is in that specific section? That thing I keep talking about that's like, here's a thing that tells Windows what to do when I load this, and it dumps it for us. So what that means is I can take our program, main.exe, and say, look at that. And lo and behold, what you can see is it tells us exactly what we need to load main.exe. We only have one dependency. It's kernel32.dll. And if we click on it, it will show us exactly what we call in that DLL. It's virtual alloc, right? Again, that is actually specified in the executable itself. So you can actually see, depends lets you actually see that in a GUI manner. Now, we could get at it a different way. I believe dump in slash, can I get imports? Imports, here we go. What we can see if we run dump in a less pretty fashion is if we run dump in on our executable, again, what that's going to do is it's going to take that executable file and it's going to look at it and grab that section that tells Windows what to do and tell us what's in there. And it says, here are the imports. Kernel32.dll is required, and the symbol that comes out of it is virtual alloc, right? So again, this is just basically the exact same thing that the linker does at link time. The dynamic linker, hence the name dynamic because it happens at runtime, the dynamic linker in Windows does at runtime. So when our executable comes in, it performs the exact same function, which is patching in missing symbol addresses. And it does that by mapping in the various dynamic libraries we need and wiring up, so patching in those call sites to point to the correct location in memory where that function actually exists. Okay? So we can see this happen directly if we step into our code, right? Here, for example, is that call, keyword pointer, and this call goes to virtual alloc, right? You can see it happening right here, and here we end up in the code for virtual alloc, right? But if we actually look what's in our executable, it doesn't look like that, right? If we do a disasm of the executable, main.exe, you will notice that we actually see no such thing. Instead, what we see when we look at this call to the, this is the location that we just stepped through. That location here, 4000, 2000H, right, is actually, can we get that? I don't know if we can actually get that. We can't actually look at the depends piece of information, can we? How can I? Well, this is the actual piece of information here. I'm trying to think if I can get dump in to show us. I know we can definitely do this. I just don't know how. This won't help us at all, so I don't know why I'm typing it in, because we don't have any of that in there. Well, I guess here's what I could do. Okay. So let's just look at what the executable contains literally before it is loaded. Okay. Here is the executable in a hex editor. You can see the MZ prefix, which is actually the tag, the header tag that actually says that this is a Windows executable. You can actually see, if we actually look, where is my web browser? There it is. This is actually what they're called. They're called MZ executables, right? And what you'll notice is this is MS-DOS executable. It says this MZ executable is actually the preamble. You can see that it says this program can't be run in DOS mode. What this is actually a DOS program, an MS-DOS program that Windows still, for legacy purposes, inserts at the front of a linked executable. Not making this up. Such that if you were still to run it on MS-DOS, it would give you an error that says that this can't be run in DOS mode, so that you know you have to run it in Windows, right? Again, this was when they initially made the transition. They spec'd the Windows file executable format to have the DOS executable at the beginning of it, so that it would print that error message properly if someone tried to load the exe from DOS mode. It was a backwards compatibility feature, so that's what that's doing there, right? You can also see the Rich G here. I don't know the story behind that. I don't know who Rich G was. Let's find out. Does it say? I don't know. I'm not sure what the Rich G comes from. Someone from Microsoft can maybe fill us in on that. Anyway, maybe that's someone's name. Maybe that means Rich Graphic. I don't know. Who knows? Point being, that part of the MZ executable, that part of the executable format is just the DOS preamble. That's a piece of code that's designed to, because MS-DOS programs had no dynamic linking. They just started at the first byte of the file. They just loaded it in, pointed at the first byte of the file, and go, right? And so that MZ executable just starts at the beginning, and that's what's in there, right? As far as I know. Well, no, that's a lie. That's totally not true. The MZ part is loaded and actually checked properly. It just doesn't have a dynamic linking. It starts further in. Obviously, it can't start executing at MZ yet. So I think that what I just said is completely wrong. But you can see that there's hardly anything in here, and that's because, again, no dynamic linking has to occur, as far as I know, for this to happen. It can just do a straightforward interrupt to print out stuff to the console. So I don't think there's anything in particular happening there other than just the code starting somewhere in here. Again, has been a long time since I've done anything DOS-wise, so don't quote me on that. The PE here is where the executable actually starts for Windows in earnest. And so you can see it's called a PE, portable executable format. That's where this actually starts. This is the Windows part here. These are the segments, the R data, data, P data, and so on. And here is actually all of our code existing in here, right? What that means is that in this file, we can see what our code actually looks like before the Windows linker does anything to patch it up, right? So if we take a look, if we step in here, go ahead here. Here we go. So if we step in here and we see this, this jump, what we can see is that jump there. that jump there, you can see it's getting the address from this location, right? 13fe0200h, right? That is something that's in our executable that we have stored. And it's doing very much like we did, where it's getting a 64-bit, I believe, jump out of that. So if we take a look at what's in there, let me do this. No, not 9x. There we go. So if we assume that this thing right here is a pointer to a 64-bit value, then we can see what that value actually is. And it's 778D5C40. That's where it is, right? It's at that location. And what we can furthermore tell is this address, right? Where is that relative to the start of our code? So here's where the code starts, right? This is where our code starts, right here. Where is this relative? I just want to know where that is, right? I just want to find out where that is relative to it. Oops. Here we go. So that's 4,000. That's 4032 away. So it's down here somewhere, right? It's down in this 13FE0200, right? So let's go down there. You can see that it is. There it is. All right. So you can see where that is. It's right here. And this is getting disassembled as actual code, but it's not, right? This is the same trick we used. So the disassembler thinks it's code. It's not really code. It's actually the address. It's actually this address, right? Why did you do that to me? I went all the way down there for a reason, debugger. There we go. You can actually see that address 7. So it's 45C8D, 45C8D77. This is the same trick we used, where it just stored the pointer that it needed to jump to. It stored that out here in sort of the part of the code where addresses for dynamic linking are going to live. Okay. So what we want to know now is, was that ever in the actual code? Was that ever was that in our executable, that address hard bound? And the answer in this case should be no, although this is taxing my knowledge of whether kernel gets special linkage because it's kernel, but assuming that it's not. What actually presumably happened was that the dynamic linker patched this up from some other address that wasn't actually there to begin with. And what we do know is we know that it's from the start of our code. We do know how far away it is. Like I said, it's 4032 away. So what we might be able to do here is take a look at main.exe and figure out if we can locate our actual code. So FF15A3OF, for example, is code that should just exist in here somewhere. And I'm going to search for it. FF15A3OF. Here we go. And let's see if we've actually found our code. So here's FF15A3OF, right? 00 is right, 4849. So this is our code. This is on disk, our code, right? And so from the start of this segment here that we looked at, which was actually here, and furthermore, we could just look at 1000, because 1000 is probably where this actually started to a certain extent, right? It was probably loaded into this page. This is probably nonsense here. We probably got loaded there, right? So if we take a look at this this code page, right, at some point we would assume that we would get down to the location where we would have been loading that pointer from, and that pointer should actually have a different piece of information in it. Now you can see, we can even see just right here that this is the table that tells us what we needed to load, because you can actually see it right here. It's kernel32.dll virtual alloc, right? So here's the table that tells the Windows linker what to patch. But the question now is, where is the actual value that got patched, and what was it, right? And that's going to be a little harder to find because it's probably just, again, zeroed out or something in here. So I'm not sure. Anyway, what I'd love to be able to do is actually see before the Windows linker actually does its patching, but I don't really know any way to do that. Like, I don't know how to stop Windows from how to inspect code before the Windows linker gets to do it. So what I'm going to do instead is I'm going to try here some things that are not super advisable. I'm going to try some amusing things to do, if that makes sense. So I'm gonna try and locate this using some more hand wavy stuff, right, in the actual file. Although I guess, you know, the other thing that I probably could do, I could probably use dump bin to guide me. So let me actually try that instead, because that would be less ridiculous than what I was about to do, which I don't think we should do. Okay, so let me go ahead and try here. How do I get to my desktop? There we go. Load that up. Let's come in here. I'm going to go ahead and call dump bin, and I'm going to take a look at the imports from main.exe. And I'm just going to see if I can get it to tell me. So you can see here, right, these are the two pieces of information that tell me where in the code, in the absolute addressing of the code before it's had address space layout randomization applied to it, but in sort of the canonical addressing of the code where these two things are, which correspond actually fairly reasonably, to where we're seeing them here, right? You can kind of see the import address table is at this location, and the import name table is just a little bit ahead of it. So you can see here, here's the name table, right, is here, and it's only 50 bytes. I'm assuming, actually, I guess this is probably in hex. So it's 0x50 bytes back is where the actual pointer table is, right, where the actual import address table is. And so in this stuff right here should be where that is stored. That's my guess. Now, I don't know if I can get it to tell me any better than that, like where it actually is in the output file. Let me see if I can get it to give me something a little bit better. And again, I apologize, I'm kind of rough at this sort of stuff. Let's see here. Okay, so this is pretty good. This actually gives us the raw data, which is exactly what I want. Okay, so that's perfect, right? Okay, so in this case, right, we can see two pieces of information. Here's this raw data number 4 and this raw data number 1 are not the interesting part. It's this raw data number 2. How do I know that it's this raw data number 2? Well, the reason I know is because when I looked up at what the imports were, you can see that it said the import address table was at this location, logical location, and the import name table was at this logical location. Now, again, these are not the locations that are actually going to be in code. These are because of address space layout randomization. These are sort of the recommended base address. So I guess one thing that I never quite mentioned was whenever the compiler compiles something, whenever the linker links something, it links it with an understanding of what the base address probably will be. It picked, it looks like 140000000, right? And you can see that everything that it generated is based off of that base address. So when it does a dump bin, it's just saying, hey, this is where I expect this thing to be loaded in memory. But of course, Windows will randomize where it actually gets loaded. So now that no longer corresponds. It used to be that majority of the time in Windows when you ran a program, what you got in dump bin was exactly where it would have ended up. Not true anymore. So you can see it's slightly off, and that's because of that address space layout randomization. Okay. But putting that aside, so now we know that the address import table is at this location. Here is the address import table. This is it, right? We also know that the import name table starts here. So here that is, right? This is the import name table. And so what's happening is this value here, right? And we should now be able to figure this out because we can now do sort of a delting from the bytes that we see in the code here in the raw data and where they are here. We should be able to actually do sort of a delting there to figure out where it actually is relative in the code, right? So let's actually see if I can do that to a certain extent. I'm going to look for the 894C2408, right? That's what I'm going to look for in here to see if I can find it. And maybe I can, maybe I can't. Or actually, you know what? I could probably do it the other way around. Let's look for the FF15 part of things here. So here it is, A30F. So that is this piece of code right here, right? And so working backwards from there, if I just kind of go backwards in code bytes, I should get back at some point to the first actual instruction that I see here in this page, which is at the 40 part, which is right here. So that's 4083 EC38. That's that piece of code. Okay? So if I take a look at where that loaded, so this is the location that that piece of code loaded at, I know that this is the place where I'm at in where the linker just guessed if the base address started where it thought it was going to start at the 14 million or whatever. 140 million hex. It's not, you know, OX 14000100. What I can do now is look at the delta between these two and figure out where that, where it corresponds to in this universe, right? So let's go ahead and look at where we're calling here. We're calling at 2000, right? That's the location that we're looking at. And again, so if I was to take this location, which I did originally, the 1040 there, the start of the code, and subtract it, it's 4032 away. I want that in hex again. That's FC0, right? And so what I want to do here is I want to know, well, if I was to start from here, right? 14OX14000 1040. If I was to start from there and go that far forward, right, go FC0 forward, where would I end up? And I'd end up right there, right? That is literally the start right here. So now we know definitively, in our executable, this is the address, 6020000000000000 is actually what was there, right? But that's not what's there anymore, if that makes sense. When we actually look at what was there, we find something totally else altogether, which is what Windows has patched in. So we know that Windows is now overwriting that value by using this table that's specified starting here, encoded in whatever format it's encoded in. We could actually go look up this encoding and actually decrypt that, but this has been an incredibly long stream. I think I want to say I started this stream at 2:30, potentially, maybe 2:15. I think this has been probably one of the longest streams I've ever done. So I won't belabor that point, but that's exactly what is happening here, right? It's using this table, which is information that actually has strings. It's matching those strings to the actual DLLs. It's patching in the address so that it can jump into the DLL, and that is what's happening, right? And so somewhere in between when it gets loaded and when we actually get to start in the debugger, that patch up occurred, which is why when we go and we look at where we jump to this value here, even though that value was nowhere to be found in here, right? There is that is not encoded anywhere in our executable. Windows is patching that in using this table. Okay. So now that we've done that, we now have a complete understanding of exactly what is going on in all of the Handmade Hero stuff. Okay. From what I've given you today, you can go and apply it completely to Handmade Hero. How? Well, here you go. We know in Handmade Hero we produce two things. We produce one executable and one DLL, right? The executable is the Win32 platform code. The DLL is the game code. We use Windows's dynamic loading capabilities to load the dynamic DLL in, right? That's what we do. And when we load the dynamic DLL in, we know that we have to get some location of code to jump to. And how are we going to do that? And the answer is we use the exact same process that Windows uses to figure out where to jump into our executable, right? It's these tables, right? These tables are written into our executable and say stuff like where the entry points are, or if we have named functions like virtual alloc, like the DLL does in kernel 32 DLL has, it knows that there's specific named entry points. So what is that? It's get proc address. If you go back and look at the Win32 stuff, get proc address is a thing that says, hey, Windows, using all the mechanisms that you use for dynamic linking, tell me where does this name exist? What entry point, what function pointer would I need if I wanted to start executing at this named entry point in this DLL, and it will return back using exactly the same tables that we're looking at here. It will return back, here is where that is, right? When we do that, we are then able to jump to that function, right, as a function pointer, just like we were doing before. So it just gives us back an address of that DLL. Furthermore, when we call into that DLL in Handmade Hero, we pass it function pointers that point into our code. Again, no difference here. All we're doing is passing those function pointers into that code so it can call those function pointers itself using exactly the same stuff, techniques that we showed today. That code is just code in memory. The pointers just point at the locations in memory. We wanted to be able to provide them to the game code DLL. We did that by bundling them up in memory and just passing it a pointer to that memory. And that's it, right? So let's take a look at that in a little bit more detail. Let's go into the Handmade Hero directory, right? The build directory, actually. And here is the code that we build for Handmade Hero. Here it all is, right? And let's take a look at the Win32 Handmade stuff using dump bin, right? So if I actually take a look here, I don't know that I want to disassemble this because it's going to throw way too much stuff at me. Yeah, this is going to throw way too much stuff at me as well. Stop, 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 stop. Bad. No. Stop. Please. Oh my God. Just no. Well, ladies and gentlemen, here's a nice printout and me hitting Control-C repeatedly and not getting any ability to stop it. How about we just close this window? That seems like a good compromise. All right. Try that one more time. This out of here. There we go. Go into the Handmade directory. Sorry, the build directory. And let's do a more modest look at the imports of Handmade Win32 handmade.exe. And so to start out with, you can see the Win32 Handmade links to a bunch of things: user32, GDI32, WinMM, OpenGL32, kernel32, right? And you can see all of the entry points we use. Now, you can see this is much more involved than the one we were looking at before. Why? Because Handmade Hero calls the operating system at a bunch more entry points, right? So it needs to map all of these DLLs into its address space. At startup, Windows will map all of the code for those into our address space. So we have, our code, we have GDI32's code, WinMM's code, OpenGL32's code. All of that gets mapped in there. And then all of these names get resolved, so it all gets wired up. So everywhere there was a function pointer to say get device caps, it is now replaced with the actual address of get device caps, so that it can execute that call properly, right? But that's all that's happening there, is that's getting wired up. Okay. So then we can look and also look at our handmade.dll. What does it import? So what you can see from the imports of the Handmade DLL is basically the stuff that's there is just the necessary stuff for DLL, the C runtime library's DLL stuff, right? So this is all this is all called from the C runtime library because we don't call any of this stuff, right? When we remove the C runtime library, eventually all of this will go away and there actually won't be anything here. So the more important part for us to look at Handmade DLL is the exports part. And you can see here is what we export. Again, these are the tables that Windows wrote into the DLL, or the linker wrote into the DLL that Windows can read. And when we call get proc address, it will look at these to figure out where in this DLL, in the executable code of this DLL, these things start, so that they can patch up things that link to it directly. But we don't actually do that. What we do is we call get proc address. Get proc address just looks at this table and returns where these actually are, right? OK. So all that's happening when we do our load library on Handmade DLL in Win32 code, it's being mapped into the address space of the Win32 Handmade executable. We are then calling get proc address, which searches the table in the DLL for that name that we're looking for example, game get sound samples or game update and render. returns back a function pointer, which again is just an address that says where in this, it mapped it into our process space. So at some point it loaded Handmade DLL, put it into our address space. Where in our address space is the actual code? Off it goes, right? That is all that's happening. Now, hopefully you're very comfortable with function pointers. All that stuff should seem very non-mysterious. The only thing we haven't covered is how those tables are actually stored. Again, those actually can be described in here if you want to see them. There's a whole bunch of information in here about how relocations work. You can see in here you've got import table specifications and stuff like this. You can actually see that stuff is all rigorously defined. I don't know the best place for it. If there's a spec for this out here somewhere, here it is. So you can look at these, and in the spec it would tell you exactly how that was laid out, for example, and go from there. Also, probably the Matt Pietrek article, I expect this probably is a good tutorial on it as well. Oh, and here you go. So Matt Pietrek writes pretty good articles about this sort of stuff. He's like one of the Windows internals guys, right? I believe. Yeah, he's the Windows internals guy. So if you want something that's less dry, his articles would probably tell you all about how that stuff is encoded in there, right? But again, it's really academic. All you really need to know is that there's some kind of binary encoding, just like the kinds we develop on Handmade Hero for storing art assets. They just encoded in binary something that says, hey, I open the file, I got to look at the file and go, okay, where's the table? So I need a header that tells me where the table is. I go look at the table. The table says how many entries it has in it. For each entry, it has, like, here's how long the name is. It has the name and where it is, right? It's that kind of stuff. So it's just the same things we're doing on Handmade Hero. The Windows dynamic linker is doing the exact same things, opening up an executable file, reading that file into memory, right, and looking at the tables to figure out what it has to wire up. It's nothing mysterious. It's stuff it's the exact same kind of code we've already done in Handmade Hero. So once you've got that, right, once you've got that happening, the only real thing that I wanted to point out that underlies all of this, and that we've never really talked about explicitly on Handmade Hero, is the notion that the CPU is executing code somewhere, and the notion that there's a stack. And I don't want to go into those too much detail because this has been a huge amount of information to cover in one session, but hopefully it was a complete enough explanation that now function pointers are demystified, to a certain extent anyway. I just want to cover one brief discussion of how that works to ground it a little bit for you, and maybe some other time we can go into more detail about what these things mean. So what I want to do is show you now, looking at this code, first of all, I want to explain what it means to say that the processor is executing code somewhere, right? And what it means to say that a call is relative to our location, right? Those are kind of like nebulous words. Well, what I want you to do is look at the register window in the debugger and pay attention to this RIP. Okay, this is one of the registers in the processor, RIP. And what hopefully you can see is that the address in RIP is the address we are at. And when we execute an instruction, RIP advances to the next instruction. This is actually how the processor is tracking where it is executing, right? Quite literally, if I say what is the value of RIP, it is always the address of the instruction that I am currently executing, literally. If I were to change the contents of this register, I want to go back an instruction. So I cut and paste into here the address like so. I move the instruction pointer, literally. You can see that I just did it, right? Let's move it back further. I don't know. Let's move it there. I don't even think that's legal what I just did, but that's what happens, right? I just moved it to some totally nonsense location, and that's just what goes on, right? So when I say the processor is executing at a particular location, what that means is actually very concrete. It's not abstract. There is literally a register in the processor. That register literally contains the virtual byte address. Again, this is in the process's address space. So it goes through the virtual table. It's not a physical memory address, it's a virtual memory address, so it still goes through the mapping table to virtual memory. But it holds the virtual address at which code is being executed at that time. And if the value in that register changes, it is executing at a different place, period. The definition of executing an instruction is to read what is at that location and execute it according to the rules of x64 instruction encoding, and to advance RIP by the number of bytes it consumed every time. That is all we are doing, right? So when I say that this call encoded the location relative to the current place, what I mean to say is that after it consumes the bytes of this call, RIP will have advanced by that many bytes and is now at a particular value. The value that you put in here is quite specifically, or sorry, I shouldn't say that value put in here. This is the translation of it. The value that you put right here in the actual instruction encoding, the value that you put right there is literally the delta between what RIP, the register, equals after the instruction has been decoded and where you would like it to go. It's the delta, right? This is actually called RIP relative addressing, I believe. Excuse me. Because it is addressing relative to RIP. And what it means is that when you have instructions that support RIP relative addressing, you can encode, instead of an absolute offset, an offset relative to the instruction pointer at that time. Okay? Also, same thing with the stack. The stack, which we always talk about, what is the stack? I need to set up the stack, adjust the stack, blah, blah, blah. The stack is just, by convention, there's nothing really magic about the stack other than I believe push and pop calls have built into them an understanding of the fact that there's a particular register that stores the stack. But other than that, the stack is meaningless. The stack is just a convention that's obeyed by when code is generated. Point being, RSP, the register, is just the pointer to the program stack, the code stack, right? So all the time when you see things addressed on the stack, it's just RSP plus some number. Right? So it's saying here's where the stack pointer is at, and I'm going to reference off of that all the time. So again, the stack and the instruction pointer, the stack pointer and instruction pointer, are actually just registers that are just there. There's nothing magical about them either. They're just numbers that store where in the virtual address space stuff is. That's it. So none of this is mysterious at all. There's nothing weird about the relative to where we are or what we are means. It's very concrete. The RIP register stores where we are, and when we say we're going to be relative to where we are, we just mean RIP plus some number. Okay. Let's go ahead and just and go to a brief Q&A here. I hope I've covered everything that you might want to know, but I'll take some questions in case there were things that kind of slipped by. So let's go ahead and do that. I think HDBot or whatever is dead, so I can't. Oh, it's not dead in the Handmade Hero chat, but it is dead in the Twitch chat, I guess, for whatever reason. So pseudonym 73, also known as our resident math expert, is saying that www.iecc.com/linker is worth a plug. And if he says so, he's probably correct. But I don't know what that is. Oh, it's a linkers and loaders thing by John Levine. So let's try and get that up on the screen there, because that probably is a pretty good thing to know. www.iecc.com/linker. Here you go. Here's the chapters of that book that talks about all this stuff. Look at that. That's great. So this would be a great thing for Marine that go into a lot more depth than I would. But why not? One says, technically you need to call flush instruction cache when you generate code. I don't think that's actually true, is it? You only need to call flush instruction cache if the instruction cache could have had those instructions in it, which if you've never executed the code before, it can't, right? So is that actually true? I suppose maybe it's true because virtual alloc could have given you back a thing that was well, but so that's a good question. I don't really know. Maybe you do, maybe you don't. I don't really know. That's a really good question. Well, let's talk about what that means. It probably is true that you should call it, because if it may have had that piece of memory in previously for another reason, well, I'm going to say what this is, and we'll leave whether or not this, in this particular case, you actually have to call it as an exercise for the reader, because I'll be honest, I really don't know if you do or don't. I would suspect that you don't, in this case, need to call it, but that may not be true, because it may be the case that, well, yeah, I mean, the instruction prefetch maybe could hit it before you got there or something, and then be wrong. I don't know if that's how that works. My knowledge of the x64 CPU is simply not good enough to say. So I'll just simply say what this is talking about and why you may need to call it or may not. We all know from talking about it on Handmade here, obviously, that data always goes through a cache, right? In the processor, there's this cache sitting there. And the reason for that is because, typically speaking, when a processor touches a piece of data, it's probably going to touch it more than once. So usually when the processor goes and does some operation on memory, nowadays it goes through a cache. The cache is designed to be a smaller version of memory that's faster to operate on. So things move into the cache, much like they move into registers, which are even faster. It's kind of like this tiered system of things come from memory to L3 cache, to L2 cache, to L1 cache, to registers, back out to L1, L2, L3, and so on, right? We know how that works. Well, the same thing is true for instructions. Instructions actually go into a cache as well. And the interesting thing about this cache is this cache may actually not store the actual contents of the instructions. What this cache actually stores potentially are the micro-ops of the instructions. So there's actually different kinds of caches. There's caching the actual bytes of data that form the instructions, and that's one way that the instructions might be cached. But there's another thing called a trace cache, which a processor can have, which is a thing that actually stores a more specific decomposed version that the processor's already looked at and potentially stored in an even more decomposed form than the assembly language. So something that's more specific to the processor and how it's going to execute it. So there's actually multiple ways in which code can be cached. It can be cached just in terms of caching the memory, but it can also be cached in a way that has actually sort of disaggregated the code into smaller pieces, like micro-ops that the processor actually wants to operate on. So there's multiple ways in which codes can be cached. And if the processor is not smart enough in a particular circumstance to know that you have modified a piece of code and that it needs to invalidate its cache, you can tell it. So that's what this function is. It's flush instruction cache. And basically what it does is it says, I'm going to give you a pointer and a size, and I want you to take everything that's in there and assume that you're going to have to refresh your caches of that if they happen to be there for execution, right? And so if we wanted to do that, what we would do is after we generated the code, we would call flush instruction cache with the, actually I should put that up here as well, because this is another one of these. I believe this is an int unsigned. Don't quote me on that. This is a handle. This is a LP void. And this is another one of those size T's. Okay. So there's our flush instruction cache, and we're going to have to deal with this definition of handle in a second here. But then what we're going to have to do is we're going to have to pass flush instruction cache something for that handle, but then we're just going to be able to do exactly what we did for our virtual alloc. So we can pass that and the code size. So what we really want to do here is just say how big is our code page. So we'll say code page size, and we'll just say 4096, and then we'll say OK, pass that here, pass that there. And that will flush the instruction cache. Now the handle in this case, for our H process, again, we sort of have this problem of where are we going to get that from. And furthermore, we need a way to get our actual process. I believe I showed this on Handmade Hero, but the get module handle function actually will do that for us. I don't know, can we pass 0 for that? I should have double checked. I don't know if we can. I don't think so, although sometimes you can and they don't say. So I don't actually know, but I'll go ahead and do the full version anyway. Get module handle gets the process handle in Windows of the particular process, and you can pass 0 for the module handle name there. So in this case, we've got this, like so. Long pointer to a string, module name. There we go. And so I'm going to go ahead and just pass get module handle 0 here. And so the only thing that we really need now is a definition for these two things, of handle and of H module, which we don't currently have. But again, I can do the exact same thing I did before to get those definitions into our program here. And if you're wondering why I'm doing this instead of just pound including windows.h, it's because I wanted to keep it so that we are completely in control of the process, and we are providing all of the code that's actually getting compiled, because that's kind of the low-level sort of stuff that we were doing. So here, if I do get module handle, right, and I ask for the definition of that, you can see here that it goes to ASCII version there. And let's take a look at the H module definition. Go to definition. You can see that there's a bunch of typedefs here. It's actually an H instance is what that is. And declare handle is used for that. We need to go to declare handle. And you can see that basically it's just an anonymous struct with an int in it, right? That's about all that's happening here. And so if we want to create one of those, we can pretty simply by just saying, OK, really all we're talking about here for a handle is this. And I believe it doesn't matter at all. These are just things that these are just dummy structs, dummy ways of talking about an int. Right? So I believe we should be fine here. Oops, got to have that semicolon there. And now our get module handle, unresolved external symbol, is that really true? Right. It's because we need the ASCII version of that. There we go. It doesn't really matter which one we have there. There we go. So now we can call flush instruction cache as well, which, again, I don't really know that in this case we absolutely needed to do, but it's a good point to bring up regardless. So if I come back here to our code here, we should now be able to call both of those functions. So here's the virtual alloc call, right, that's calling through here. Then we're going to generate all the code. So here's all the code gen, et cetera, et cetera, et cetera. Then we're going to call, I guess after all the code gen, we have to call get module handle A, and we have to call flush instruction cache. So let's take a look here. There we go. I believe that's the get module handle, although we should actually look at the dump bin to verify that. I believe this is the flush instruction cache. Is that actually correct? Let's take it. Let's look at the dump. I don't want to say that because I have to look at that a little bit. I have to look at that a little more closely before I would be able to say that that was true. Cannot open input file. That's because we're not in the right directory. There we go. All right. Let me actually look at that. OK, so yeah, you can see here's the call get module handle A right there. And there's the flush instruction cache. So if I actually come back here and take a look at it and kind of scroll down past all the code filling out there after the LEA. There we go. So there's the LEA, and then there's the call to get module handle. So there it is, the call right here. And what you can actually see here is that it's, again, there's that the linker has patched it, right? You can see that the patching happened there because before there wasn't anything here, and now there is a 73, right? So there's the patch that the linker did. And then similarly, here's the patch again. And you can see that these were indirect patches. So the linker probably patched this one, and then the dynamic linker patched this one, right? It patched this right here. So it's kind of a double indirection, right? And in fact, that's when you've got a bunch of these, you can see how it decided to do that. So instead of welding that call in directly, it did a double indirection there. But there you go. Let's see. Insofar as says, I think something like /section : .data /rwe and /nxcompat : no to linkxe might work for the non-virtual protect code in array thing. So yeah, like I said, I don't really know. You might be right. In theory, the executable has in it, here are my data sections, here are my code sections, here's how I need you to mark those when you load them, Mr. Windows, right? And I guess the thing about that is just that, yeah, there's probably a magic incantation that lets you say, I want my data segment to be executable, please. But I didn't want to try and figure out what that was. So that may be right. I have no idea. But there almost certainly is some way to do it. Nacre314, who is the person who originally asked the question, maybe this episode belongs to the intro to C Week as episode 6. Maybe. User 549, maybe the smallest CRT ever, and it's a link to something. Let's see here. Philadelphia says, is there a low-level reason you don't like virtual functions? My understanding of them is that they're basically just function pointers in a table that is dereferenced. Yes, there actually is a low-level reason I don't like virtual functions, and that is that they are unserializable. So one of my main complaints and furthermore, I can't patch them, right? One of my main complaints with the way C++ does virtual function calls is it's an opaque system. So you're not allowed to specify how it's working. You can't say, for example, that what you want to have inside your structs or classes is just an integer that says what class it is, and then that integer looks up into a dispatch table somewhere else or something like that, which would be serializable, for example. So low-level wise, virtual functions are just not very good, right? They don't give you the control that you need, that you have if you actually build your own function pointer tables, because you can do anything you want there. You can have them be double dispatch, single dispatch. You can have them dispatch off an integer that you control that's serializable. You can put it anywhere you want in the struct. You can get rid of it in the struct if you don't need it because you can infer it from something else. So yeah, like I don't really like anything about virtual functions, right? They're a bad feature because they take control away from the programmer that they actually need. There's a good way they could have done that in C++. They didn't do it because they chose not to give you the control that you need in order to write code that's flexible and interesting. They chose to go with a really Procrustean version that takes a lot of away a lot of the power that you get if you're actually using function pointers yourself. Engineer says, first of all, thank you so much for this stream. You are very welcome. At the beginning, you mentioned you hadn't done some of these things for a while. My question is, in what context did you originally learn and apply all this information? It seems like spending time at work exploring this may be considered time taken away from actually being quote-unquote productive. Is it just something you have to learn on your own time? I guess I would say that it depends on the place that you work for. You know, if you work for a company that values low-level programming skills and people who can debug very difficult problems and also create creative technical solutions to things, they should value this quite highly. I cannot imagine the situation where Jeff would have come into my office at RAD and found me looking at how something was happening in a link loader and telling me that I was wasting my time. He probably would have been delighted and probably would have helped explain it to me because he's a very talented low-level programmer. And so that's just the nature of where you work. If you work at a company whose like main job is to like stack Python on top of JavaScript on top of 12 piles of libraries 10 high to get sort of some weird thing working on top of the Google Maps API, yeah, they probably have no interest in you learning the stuff, because when would it ever come up? And it has nothing to do with getting the next round of venture capital or whatever. It just depends on the attitude of the company you work for and what their priorities are. I can tell you that it would be very rare for you to go to an engine development company for games and have somebody tell you that learning this stuff is not a good use of your time at the company, because this is definitely a good use of your time, right? But if you're at a higher level than that, I could easily see them saying that, because it's not relevant to what you do there, right? And so it's all dependent on what your job function is and what you're doing. Furthermore, I would say that in the web development context, I think this would also not be a waste of your time if you're somebody whose job it is, let's say, at Facebook, to do like back-end stuff where you have to optimize like some crazy huge amounts of PHP code that's coming in, and you're trying to write this like compiler thing that's going to make your stuff perform better because you've got all this legacy code that needs to execute or whatever. Even if you're doing web development, there are places in web development where the metal, or what do they say, the rubber hits the road, if you will, and those people need to know all these things. So, the people who are powering the Google search backend, base level stuff, and the people who are working on optimizing, Facebook's file IO stuff or whatever, they all need to know this stuff. And I don't think those divisions, even though they're in companies that are piling libraries on top of libraries on top of libraries, that's one part of the company. There's usually going to be a part of a company that cares a lot about low-level programming. Those people would not consider this a waste of your time. So I think that's it. It doesn't look like we have any more questions, so I think I will just wrap it up there. That was an incredibly long Handmade Hero stream, to say the very least, but it covered just about everything that I wanted to cover, and hopefully it answered the original question well enough to say that basically now, like, all of the parts of it are demystified, hopefully, and there isn't any sort of like hand-wavy weird thing happening where you're not really sure about what's really going on, right? So anyway, hopefully that is everything there is to say about that in terms of an introduction. Obviously, there's loads more you can explore on your own. I do appreciate that link from Pseudonym73, which I bet is a great place to investigate more about that if you want to learn more about dynamic linking or static linking and all those sorts of things that we talked about. So please do check that out if you're interested in more, or post on the forums. And that's about it. So thanks for joining me for another episode of Handmade Hero Chat this time. If you have questions about the sort of stuff we covered, you can ask it on the forum site. And that is about it for this week. Next week, we will be back to do regular game coding again. Until then, have fun programming and exploring some hopefully low-level code stuff on your own. And I'll see everyone on the internet. So take it easy, everybody.